Right, let's see if we're live. Just give it a second and see if we get a bit of response. Yep, I think that's us. We're now live. Right, this will be interesting. So, for anybody who's wondering what the hell's going on, most of the people in the panel are wondering what the hell's going on as well.
Indeed.
I just basically contacted everybody off the cuff and asked them if they'd mind joining me on a panel. I didn't really give them much explanation of why. And everybody's been, really good enough to agree to come along. So before I explain why, do you guys want to take turns introducing yourselves? Would you like me to shout out your names?
Yeah, shout us out.
Okay, we'll go with Bob first. Cheers.
Well, hi, and greetings from Northern Michigan. This is Bob the Science Guy. I decided to do this one outside just because it's a beautiful day here. Glad to be here.
You know I'm in Scotland, right?
Yep, and I'm not.
Yeah.
There's a reason for that.
By the way, Al, do you know you're not showing an avatar at all? You're just showing a grey thing.
A grey thing?
Yes. You've got your camera covered and there's no avatar of you. It's just a grey, foggy Scottish mist we're looking at.
Good stuff.
It's a picture of the sky.
Got it. Hold on. Anyway, continue. Dave, would you like to introduce yourself?
Sure. So I have a channel called Professor Dave Explains. I do curriculum-aligned tutorials, so I cover subjects. I cover chemistry, biochemistry, physics, astronomy, math, things like that. And only lately have started delving a little bit into the flat Earth community. I made one or two videos that attracted some attention from flat earthers. So now I've got sort of one foot in this conspiracy camp as
Run
well.
now.
Yeah.
Okay. MC Toon, you're next.
Yeah, I'm MC Toon. I have a channel where I mostly address flat earthers, though I'm gotten into some other stuff lately. And I do a lot of live debates to try to keep it civil.
You do a good job of doing that, by the way.
Thank you.
I think that's one of the things I struggle with the most.
Yeah, it's been a challenge sometimes, but if I step back and say, I'm just doing it for entertainment, then it helps a little.
Okay, Soundly.
Yes, my channel is Soundly. If you've seen any pictures of Lake Pontchartrain Causeway, they're likely mine. And mostly my channel has been about doing real-world observations, showing curvature. And as of January, I think I've pretty much felt like I hit a milestone where I didn't really need to do much more, and I haven't. So I've mostly just been lurking in the Discord channels and paying attention to other people's stuff, but not really producing a lot of content myself.
Thanks. Rumpus, you know the drill, sir.
Yes. Well, I've got a channel called Rumpus. I must admit at the moment I mainly participate in debates about flat Earth and things. I've come from a background of dealing with atheism and science in general, sort of debates and things. And I'm in the middle of what seems to be a 200-page website on refraction is one of my specialities, and Earth curvature and observations. And along with someone called Philip, we've generated a ray tracing things quite novel, actually. Nothing like it so far on the internet, which actually gives a proper ray tracing image of objects at any distance, and also gives you things like inferior mirage. It's the only thing I know of that actually models things in the real world that gives you inferior mirages and can deal with all sorts of mirages and things and gives you exactly the result. And we've measured, matched it against some real world observations of the Isle of Man, and we can generate something that looks exactly as observations are made of the Isle of Man in our model, and the match is just extraordinary. So.
Right, thank you very much. So there's one other person I just want to mention. Tommy Grønvold is in the chat. He's the moderator for the chat. So as we go through, if anybody comes up with any questions they want to ask, I've asked Tommy if he'll take a note of some questions, and then if there is some time after we've finished blathering, I'll try and ask some questions. And I'm not going to waste my time talking about myself and my channel.
That's good stuff. I'd like to point out that part of my 200-page document, whatever, features some wonderful work by Al of some wind turbines that I will be modelling and doing a lot of work on to show how it matches, the model matches it. So it's I couldn't do it without stuff like Al taking some superb observations.
Yeah, I mean, I've done a few observations. The wind turbine thing you've got is actually one of the first, and it's got that refractive band, and every other observation is lovely and clear, but everybody else gets to see the turbines. And you end up arguing with hours with people about fold lines.
I do fold lines, yeah, the ancient term to describe the separation between the uniformers.
Right, I'm going to just go over what the plan is. It's nothing spectacular. Basically, as I said, it was really an unplanned thing. I just kind of contacted you guys and asked to see if you would show up, and you're, really good. I agreed to do that, so thanks a lot for doing that. Basically, the reason I did it that way is because I didn't want anybody to prepare material for the questions that I'm going to ask. There's nothing too technical, really, no for you guys anyway, but I just didn't want anybody going away looking up specific sources, coming in with presentations or sound bites and things of that nature. I wanted it to be just, what do you know, your own knowledge and your own opinions about stuff. And then, as we go through what we're talking about, hopefully there'll be some kind of, we'll see if there's any disagreements on how you view things, if there's consensus, whatever. And the topic I have chosen for tonight is everybody's favourite, gravity. Now, the reason I've picked it is because it's one of these things that can be a bit of a contentious subject for a couple of reasons. One is the thing that keeps cropping up all the time is this distinction between Newton and Einstein. At the moment, Sleeping Warrior, who hopefully Dave doesn't know, one of the little FE puppets, he's currently doing the rounds with this kind of old argument about trying to say there's this grave distinction between the two. But I've actually had people asking me about that since I started Flat Earth a couple of years ago. It's not like a new argument or anything. It also goes back a lot further. I'm actually familiar with people, in the sort of fundamentalist Christian circles having these same kind of arguments, which is actually, I've noticed, a really common trait in Flat Earth. There's a lot of the arguments I'm familiar with from there, and I'm sure, Rumpus, you'll probably be able to back that up. Yeah. It's transferred over into Flat Earth, even by people who, don't claim any affiliation to any kind of god or gods.
I'm the resident theist on the panel, by the way.
Yes.
Oops.
No, but it's good because you're not a fundamentalist Christian who puts out all these terrible anti-science arguments, you know what I mean? That's the crowd it's coming from, the young earth creationists.
Yeah, you're not a young earth creationist, are you, Sam Lee?
I am not a young earth creationist, no.
Right.
I am a Christian, but not a young earth creationist.
Okay, thank goodness for that, so we can avoid that.
You can put me in the same camp, too.
Right,
oh,
excellent.
true,
So
yes.
That's good because that's.
Oh my God, it's spreading. I'd like me too.
I'm actually. I guess I would self-label as a old Earth creationist.
You're not that old.
But God is.
Losing the plot here. So, again, not sure if Dave is really familiar with this, but as everybody else in the panel will know, the thing that's cropped up most recently is this attempt to dissect George Musser's article when he used the phrase snapping the wand in two, which is, obviously
in the Scientific
completely
American,
misinterpreted by...
in the Scientific American, he published that, didn't he?
Yeah. So it's a kind of talking point now, but then looking at it from the other point of view, it is also contentions in the sense... we do use, essentially the Newtonian aspect for pretty much everything on a day-to-day basis, but we're also looking for ways to reconcile what we do every day with things at different scales, like large scale, very small scale, quantum, etc. So there's still a bit to learn about it and lots of research going into it. So it's still something that, it's not really a settled thing. We've got our, the things that we agree upon at the moment, but it's not a fully settled thing. So even outside of the whole flat Earth stupidity, you can still argue that it's a little bit contentious. Is that okay with everybody? You kind of agree with that?
Yep.
Right. So I'm going to kick off by asking you each in turn to just do a really quick, short answer. Basically, when I say your name, I want you to describe what gravity is in your own words in the most concise way that you can do that, without any, without too much technical jargon. Just one at a time. And Rumpus, like I said, concise, right?
God, you're really giving me a hard time, aren't you, Al?
Well, you know why. So actually, Rumpus, we'll start with you just in case. So a quick, concise explanation of gravity.
Right. Well, gravity is what we see in this world and our 3D world as the mass attracting mass, and we can see that on a local scale, like dropping a banana or something, and in the Cavendish experiment, where we can actually see the attractive force between two masses in an experiment. We can measure this, and we can determine that this follows Newton's law, universal gravitation, which he postulated in 1670 odd in Principia, and he then realised that the am I going too slowly already?
I'm just laughing. We're now getting the history of gravity in a concise
right. I just thought, perhaps I'm favoring everybody else talking this stuff. Perhaps you don't need to repeat this. I suppose it's an intro. Yes, you've given me an intro. I'm afraid, Al. So
no, it's not an intro. It was a quick one. This was a test,
sorry. Okay, I'm nearly there.
This is you being quick.
I'm going to speed up. So I'm going to speed up.
I'm
going to speed up. I've set the foundations. I'm going to move quickly now. Yes, and so in that inverse square law, which means the attraction between two masses is dependent on the two masses, the product of the two masses, and the reciprocal of the square of the distances. And that works. And even now, with the modifications that Einstein came up with in 15 with the general theory of relativity, those equations are still valid. And George Musser in his article was not denying those that force was valid, except in extreme circumstances.
Right.
And
stop.
Oh,
right.
I've gone too.
You're going way too far now.
Sorry.
Right? So
Okay.
You're preempting
okay.
the rest of the conversation for.
I'll try and finish it in 10 seconds. Then I'll try and finish it in 10 seconds. And Einstein proposed that the curvature of Earth in its 4D world manifests itself in our 3D world as a force. So anybody who says it isn't a force, which is what you'll find all over the internet, in our 3D world, it is a force, but its origins are not as a force. It's an inertial force, a bit like centrifugal force. Finished.
Thank you for that not so
sorry,
concise explanation.
Sorry, apologies.
All right. So I'm going to go down the line and pick you out. One thing I would like to ask is just, nobody say, yeah, what that guy said, right? Just your own words, okay? Well, I suppose you don't want to repeat all of that anyway, but... so let's see, in the order I can see people, I'll go for Bob next, if you don't mind. If he's here.
He's muted already, aren't you? You see, you're missing me already, Al.
Was that me?
Yep, your turn. Did you hear the question?
Yeah, something about gravity, right?
Yep.
All right. Well, here, let me put my camera on so you can see this beautiful Michigan summer day.
Oh, ha ha.
All right. Now, when I move my phone from one direction to the other, it switches from portrait to landscape. That's because it's undergoing a constant downward acceleration of 9.81 meters per second. That's what we call gravity. Now, Newtonian gravity is used to design bridges. It's used to determine flight characteristics, the orbits of planets and moons. It works just fine. It is the it is the what of what gravity does. Einstein came out and described the theory of general relativity that gives us a better idea of why gravity does that. It's the warping of space-time. Now, unlike Newton, who thought that this was just an intrinsic property of matter, Einstein actually attributed it to something. So it was no longer a magical effect. So Einstein, of course, broke the wand of Newton, and we all understand exactly what he was talking about. But the flat earth is trying to use an evocation fallacy to use a different meaning of that to somehow say that Einstein replaced Newton. So basically, that's all I have to say about it. It's, you know, my gravity is the fact that my phone flips. My gravity is that I can calculate the trajectory of a bullet. And that works just fine in our world. And you know, the other day I did a video on Quantum Eraser and his efforts to talk about gravity not being a force, where he cherry picked about 6 different scientific papers. Every single one of those papers, 2 paragraphs later, said that unless an object is moving close to the speed of sound or is you know, on the atomic level, Einsteinian gravity reverts to Newtonian gravity for all intents and purposes. So I'm very comfortable with Newton. Newton's just fine. Einstein just tells me a little bit more about why it happens. But I don't use field equations to figure out how much of a bullet drop there's going to be at 600 yards. I use Newton. And guess what? I can hit a 4-inch rock at 600 yards. So that's all I have to say about it.
Thanks. I'm just laughing because, you know, summarize and be concise, and, you know, the explanations are fine, but it's just funny. Dave, you're up next, please.
Okay. Well, to paraphrase what has been said already, of course, I would describe gravity as the apparent attractive force between all matter by virtue of their ability to warp space-time. And that's our best model currently, general relativity, and hopefully that will be refined further if we can develop a quantum field theory for gravity. So who knows about gravitons and all that. As far as that interfaces with the flat Earth community, the 2 main problems are one is a problem of science communication in terms of the whole, is gravity a force or not? This is something that is partially semantics and just way above the head of any flat earther. It's theoretical physics, that conversation. And then the other is a linguistic miscommunication. It's just, the biggest thing I get is gravity is just a theory. And so that's just the problem. That's not just flat earthers. That's a lot of people mistake the colloquial connotation for theory with the scientific definition of theory. And that's a big problem that I try to address in my content, just helping them understand that theories are not uncertain. Yes, general relativity is a theory. We also know that it is true for sure. So, yep, that's all I got.
Excellent. Thanks very much. MC Toon.
Yes. Well, before Einstein, it was called spooky action at a distance. And, you know, that kind of comforts me like a warm blanket. And I'm okay with that. When I put on my engineer hat and you got to build a bridge or do, you know, take a statics and dynamics class or something like that. As to why, well, it doesn't matter much why when you're building a bridge, right? So we don't have to explore that when we actually have work to do. But it works, right? We can measure it and predict it, and it all works. So the why, I as an engineer, I don't care. As a, you know, the next step deeper, yeah, that's great to understand why, but I don't care.
Okay, and can I just ask you, if you were actually to explain it to somebody, you know, what would you say is happening?
Well, yeah, it's hard to not say something that's already been said at this point.
It doesn't matter if you repeat it. I just didn't want anyone to literally say it. Well, he said it, so that's fine. I don't need to say anything.
So the fourth dimension, right? If we look at time as a fourth dimension, we try to figure out how it might appear. That the bowling ball on that elastic thing, if we can remember that video where the ball went around it, that's just a great illustration of what the fourth dimension would look like when you apply gravity to it, that it's bending it.
Okay. Soundly, you're up, my friend.
Well, I've just had 4 cheat sheets talk before me, so
No, but
let me try and I like putting it in my own terms because I do tend to favor intuitive explanations as opposed to technical ones, because the technical aspects will never be appreciated by flat earthers. But basically, gravity is this set of observations that we see. You know, gravity is the name that we give to mass attracting mass. That we see this behavior happening in reality. We call it gravity. We could have called it anything else. But the fact that this behavior occurs, and I'm not calling it a force intentionally because that's what they like to play games with that, but this behavior of reality occurs, we know it does, we're going to give it a name, we'll call it gravity. So to say it doesn't exist is just silly, because gravity does exist. We have real world actual historical measurements that show that gravity attracts gravity. That's what happens. That's the behavior of our reality. But ultimately, the truthiness of any theory is determined by its practical application, and that's where MC Toon was talking about building bridges. If it works practically, then the theory is good enough for now, and that's basically how science works.
All right. Thank you very much. Give me just a second. Right, so your way of talking about it sounds closer to the way I would go with it. Just if I just quickly was going to try and say what I thought to somebody, I would describe it as the phenomenon that we actually observe of objects falling, and obviously we know, having measured it, that they accelerate, etc. So, I think that's where obviously everything you need to start is recognizing that we named a phenomenon.
Well, I think it's important. I think it's important to realize the word games that are being played. And one of the word games that are being played is it a force? Is it not a force? Irrelevant. Doesn't matter. We see a behavior in reality. We see this behavior, and we name it gravity.
Yeah, exactly. That's ultimately what matters, is that, we know what it is we're trying to describe. If you disagree in the semantics of what we've decided is the cause, it doesn't change the fact that it's there.
It's quite important to decide whether it's a force or not, I think. In our world, the engineering calculations...
I agree. It's important to physicists, but the philosophical debate doesn't require it to be a force or not, and when it comes to whether or not it exists.
I mean, this is a question...
Mind if I just chime in here for a second? The whole semantics debate about whether or not gravity is a force is pointless. The reason that is coming up is that the higher functioning flat earthers realize that if gravity is real, the flat earth cannot exist. So their entire argument is based on the idea that we have to deny the existence of gravity because it destroys our worldview if it does exist. It's like admitting to the existence of space.
Well, that's
why they can't admit to the existence of space.
That's why every debate with a flat earther first starts off with, all those millions of pictures from space that you have? Okay, all that's out the window. Now let's debate. That's,
yeah.
That's definitive proof of a round Earth is not real. That's
right.
Stance. Yeah.
I'd like to ask Professor Dave a question. Actually, he mentioned the quantum theory of gravity, and I'm hoping to talk to George Musser about this actually. And if we start talking about gravitons, does that not mean to say, if we just think of it as a curvature of this 4D space-time, then does that not eliminate the need for gravitons, or these mutually exclusive? I'm not quite sure if we don't need to have the right.
From my ignorant viewpoint, the curvature of spacetime explains it just fine. If I were a theoretical physicist, I could speak further. I know that they're working on a quantum field theory for gravity, which would make gravity a force in the same way as the other fundamental forces mediated by virtual particles and such. So I know they're doing it. I don't know what progress they've made or what any of it means, quite frankly.
Can we all just agree that we're going to discuss gravity from an engineering standpoint and a practical standpoint, rather than wade in the weeds and give flat Earth wiggle room about differences in minutia opinions on very advanced...
I would say no to that, unfortunately, because there was lots of technical publications, scientific publications saying gravity is not a force. And we said we have to take this head on. We can't just say this isn't happening. And they're citing this isn't a force, so then they claim, well, how can you say it's a force then?
Then if destroy them by ask them to explain how it's not a force. Why don't you just give me the exact definition in your words,
Well, they say
why gravity is
guys,
not a
I'm going to
force
cut
and
in
what
here
it really is.
because I don't want this to wander off from the general structure that I was hoping to have, and also, you know, I don't want to be a bitch fest about flat Earth, right? So, obviously, regardless of which way you view it, and I think you're all pretty much in agreement. There are certain terms that get used when you're describing gravity, and I think part of, in a sense, settling the argument, I wouldn't literally settle it, but trying to decide where you really stand with it is partly involved in seeing, well, how do you define some of these terms and what does it mean, so that it all kind of ties together, you know, so your explanation makes sense, essentially, rather than just throwing out words. So you throw out, you know, you say something like the curvature of space-time, that might be great because it means something to you in your mind, but how do you convey that to somebody else that they understand what you actually mean by that? And
Well,
you're going to
one
get
thing
from the
that I
flat
would
Earth
add-
side is just, oh, it's a concept, you know. So I'd like to kind of talk about some of the descriptive words we use when we're talking about this stuff and see if we can kind of settle it a bit more.
Granted, that's a great idea, but recall that every of those scientific papers that Quantum Eraser used to say gravity was not a force went on to say that in our universe, the things that we can see or touch, Einsteinian gravity reverts to Newtonian gravity, and Newtonian gravity we are free to use with a high probability of success and very low error. So gravity is Newtonian gravity. Newtonian gravity is a force, unless you're talking about objects close to the speed of light or on the subatomic level.
Well, the trouble is, those papers do say, they use the words, gravity is not a force, as George Musa did in his Scientific American article, which is the one cited recently, and because he's also been on a hangout which flat earthers have seen him actually say this verbally. And then, unfortunately, he then goes on, he talks about a gravitational attraction, as though, because in their minds, that the they're saying, well, because it's an inertial force or apparent force, that therefore it's not really a force. I'm afraid I want to pin them down and say, in our world, in our 3D world, it is very definitely a force. In our reference frame, or you can think of this our world as being a projection from the 4D world, it behaves exactly like a force, because I believe a force is defined as something that causes a mass to accelerate.
Right.
And if you stick to that, then it's very definitely a force. Now, whether its origins, what its origins are, whether it's the result of some gravitons doing something, or whether it's the curvature of space-time, yes, we can debate about that as well, but we need to stop physicists saying gravity is not a force, because they're thinking in the 4D world. They're saying in this 4D world, gravity isn't a force. Because I think they're thinking the bending of that MC Toon was talking about, this bending of this idea of a bending sheet. They're not going to say that's gravity. I'm not quite sure if they've got a name for what causes the bending of space-time.
You're dealing with people that don't understand why when you lift a book and let it go, it falls to the ground. They think that lifting the book somehow stores up energy in the book that makes it want to go back to the ground.
I agree, but we've got to tackle people saying, physicists, I think incorrectly saying, gravity is not a force, because they're talking about what's happening in the 4D world, whereas we want them to talk about what's happening in our 3D world. And so, unfortunately,
yeah, if I had any influence on physicists, I would try to persuade them to stop saying that gravity isn't a force. At least in the realm of public discourse, anything that causes the mass to accelerate should be considered a force.
Yeah,
that's what I think.
Great. Yeah.
Right, so this is, you've already raised that point earlier, Dave, when you said you had concerns about the way people communicate science.
Yeah.
So this is why I had the idea of going over some of the terms more, rather than just using them, because like Rumpus did it right in the middle of his monologue there, where he's talking about a projection from the 4D world, and you're like, that doesn't mean anything to your average Joe anyway. You know,
right.
I include myself in this because out of everybody on this panel, I'm the layman, right? So,
right, but does it not give you the idea, though, that there is another world out there, and we are the projection is, I think, a reasonably expressive and understandable term that sort of manifests itself in our 3D world. And providing you've got that understanding, there's a sort of 4D world out there, and we're some sort of transformation of it in our world. I think if you understand that simple concept and hang on to that, then you can understand where in our world it's a force, and in where these theoretical physicists think of it not being force, because they're thinking in the clever 4D world.
Honestly, no, I don't think that sounds simple enough.
The Rumpus, you're trying to speak. You're trying to teach Shakespeare to people that haven't learned their words yet.
Well, I suppose trying to justify why physicists keep on saying gravity is not a force, and we need to tackle that head on. We can't just pretend this is not happening.
May I make a suggestion then?
Because it's a niche of the internet where the physicists don't even know it's happening.
But the thing is, this does extend to the layman in general, right? So
physicists don't care about flat Earth. They don't modify their language to lessen the ability of flat earthers to strike down arguments of people like us. It's not, they don't care.
Yeah.
So,
with good reason.
It's up to us to actually come up with the language if we want to do this.
Yes. Yeah. Completely
if you want
agree,
a better way to describe gravity, do it the way I did, and that is as something that results in an acceleration. When that acceleration acts on a mass, it results in a force.
Well, other way around.
Yes, the other way around. Yeah, Bob, you got it around the wrong way.
The force acts on a mass and acceleration occurs. Yeah, to me, that's a definition of a force, right?
Exactly.
I mean, that's the problem with flat earthers, is that they're so oblivious to even the most basic fundamental scientific truths like F equals ma. Like, I'll say F equals ma, and they'll go, that's not true. Like, nothing could be more true than this.
I think half of them get it. I think half of them know that.
Push a rock or jump off the grid. Like, every motion proves F equals ma. So you're denying reality right now. So
yes, I regularly call them science deniers, is my favorite phrase. Professor Dave. They just deny objectively measured science and simple motion of things, and
so we just have to come up with more and more clever ways of demonstrating these kinds of truths with the utmost clarity. The latest video I tried to be as basic as possible and as succinct and clear as possible, and I think I did about as good a job as I can, and obviously.
Am I allowed to bring up an issue with your right? Okay.
Can we not just use
now.
the acceleration? Can we not just say gravity is an acceleration? When acting on a mass, it results in a force.
No, it's around the other way.
That's relative density disequilibrium, Bob. Have you not been paying attention?
Gravity is not.
I have been paying attention. I addressed that. They don't know the difference between buoyancy and density.
But see, the problem is when you equate gravity with acceleration, then you have flat earthers say, well, why do you guys say that acceleration is 9.8 on Earth and then it's something else somewhere else? And it's like, well, because of the differing masses, right? The acceleration is not the same equal. The force of gravity is the same everywhere in the universe. The acceleration that force imparts on an object is different depending on the mass of the object that's generating the gravitational field.
That's correct, but the acceleration is measurable.
Yeah,
anybody with an iPhone or an Android.
So is the force, Bob.
Yeah.
You can measure the force with the scales. You can measure both.
Right. Before we get to off track with the initial sort of rough plan I've got. As we're talking about this, we are using a lot of the terms that I'm talking about. These terms get used, but not necessarily are understood, and I think that's part of it. So I'd like to just go over some of the terms with people and see what you've got to say about them, and I think it will form part of a general structure of seeing, ultimately what do you mean by saying, something bends space-time or mass attracts mass or whatever it might be. Obviously, in the course of the discussion, both descriptions have been used, mass attracting mass and the bending of space-time. We've also obviously mentioned the actual acceleration. And, it could be said from the outside that there's some contradiction involved in going between mass, attracting mass, and the bending of space-time. So, to understand it a little bit better, could we start with just saying, what do you mean when you say mass? What is mass?
I can answer this, if anyone else.
Well, it's just, I know there's more than one way of saying it. There's two essential answers to this that I hear, and I want to see where we all stand with that.
Well, I would say that mass is the resistance of something the mass is when you apply a force to something, the acceleration you get from that object is the force divided by the acceleration that it returns is its mass. So it's its inertial mass. Although you can start talking about the gravitational mass, but basically it's the inertial properties of something, its reluctance to be accelerated by a standard force. That's how I would define mass. So it's nothing to do with the number of atoms, nothing to do with the number of moles, nothing to do with its charge, nothing to do with its volume or density. It's just its resistance when a force is applied to it, in effect.
You just defined a thing.
Right, so does everybody agree with that particular way of stating it, or is there another way that anybody else wants to put across?
Certainly the concept of inertia has to be involved. I mean, anything without mass travels at the speed of light. So massive objects are things that don't, right? Their acceleration is proportional to the force applied on them.
So,
and then this idea, if you want to go, presumably Professor Dave could go on about what actually gives things mass, and then we get into the Higgs boson and also the virtual. But actually, the most of the mass, for instance, of a proton is not actually the intrinsic mass of the quarks inside it, but actually the interactions, the virtual particles that are created as a result of the fields between the quarks. And it's a rather complicated idea, but it's these fluctuations that actually create most of the mass, not the actual quarks. It's a bit weird.
So how do you differentiate then between mass as you're describing it, as basically a resistance, if you like, and inertial mass?
It's the same thing.
So, but inertial mass is usually used to describe something that's accelerating, is it not?
No, it could just be what it would do under a force. That's the definition. The inertial mass definition is the one that I gave. In other words, you can test what the inertial mass of something is by applying a force and seeing what acceleration it responds with. That's the definition of an inertial mass, and what we call the mass.
I think
synonymous.
It's synonymous with what we just refer to as mass, right?
Yes.
Right.
Yeah. Absolutely.
Because
relativistic mass would be a much muddier concept.
Although the term relativistic mass is now deprecated. You're not supposed to use relativistic mass anymore. Yes, that's very much deprecated now. They went out of fashion about 20 years ago.
Got it.
They just say it's acquiring this extra, and it's more difficult to move, but its mass is not changing. It's God, I'm not quite sure. They say it's more energy. That's right. It acquires more energy, and yes, I'm not quite sure what they. Yes, they don't like using relativistic mass anymore. Anyway, so in other words, M0, they always talk about the rest mass now, and they never try and think that the mass is changing. It's just that it's becomes more and more difficult to accelerate as a result of getting more energy.
Right,
but you're right, Scal. There is another definition. I can't remember what it was now, but it's related. But I think it's an inferior definition. But yes, so you're right. There is another one. I can't remember now what it is.
Well, I mean, the kind of old school way of doing it is just saying that it's the amount of stuff, basically.
Yeah, well, that's wrong. That's completely wrong.
Well, you're chasing turtles, though. I mean, you can always ask what or why in the next level.
Again, we're dealing with people who cannot understand that it requires a force or an acceleration acting on a book to have it fall to the ground. All right. I think the idea that Rumpus brought up of the inertial mass is a real good place to start. You apply a force to the mass. This is how fast the resulting acceleration is. That gives us an idea of what the mass of the object is. I think that's elegant and simple. We can't be talking about, neutrons and crap like that and quarks, because we need to look at an object,
Crap
what's
like
the
that.
mass?
Can I offer a definition that summarizes what the other guy said?
Go ahead.
Mass is the thing that resists acceleration. That's what it is.
That's the definition of inertial mass. Yes.
Yeah.
That's inertial mass. Yeah.
But that's a definition that a flat earther can understand. That's the point I'm making. I'm talking about communicating with laymen.
You have to push a rock for it to move. It doesn't just move on its own the way light moves on its own.
So, if we're going with the idea of mass being in essence a kind of measure of inertia, inherent to an object, if you like. Then we move to the space-time thing, right? So when you say space-time, what do you mean by that? Because obviously we're talking about masses bending space-time. So what is space-time?
I'll have a go.
I'm
Professor
so
Dave doesn't
glad
want
I
to
had
go
to
first.
Anybody
calm everybody down. And
I keep on going first. I don't want to Professor Dave might like to go first.
I mean, we can regard it as some kind of a fabric or substance unto itself. I can't really comment further, though.
Yeah, I don't think we really know. And as I say, I don't think the reason I think that physicists don't like talking about the word gravity being a force is because I don't know what they call the what mass does to the sheet that we visualize occasionally, that bending, right. What causes that bending? And they're not going to call that gravity. They're going to say the mass is deforming space-time. And
what is the mechanism by which that occurs? I certainly don't know.
That mechanism, yeah. What the hell is that mechanism? And it's not gravity. It's something to do. And this, of course, we haven't mentioned the fact that right. Newton, these breaking the wand is all about this instantaneous reaction. That the fact that in this 4D space-time world, that when you have your sheet and you put two things down, it's actually the bending of space-time that causes the attraction. There's no interaction between the masses to bring them together in this 4D world. It's the fabric of space-time being curved that causes the attraction.
Okay, so this brings us, quite nicely to another point, which is that if mass is a measurement of inertia, and mass can warp space-time, how does a resistance to change or acceleration warp the space around about it if a force isn't involved?
I'm going to fall back. I think it was MC Toon that put it in. I don't care. I care.
Well, that's fair enough, Bob. You're welcome to say it, but all I'm trying to do is see if anybody can chip in and just figure some stuff out. So it's not a test, It's just to see where we can go with it. That's my point. I can't.
It's well above my pay grade. I do not understand space time. I can use Newtonian gravity just fine.
No one understands space time. I mean, that's why we don't have the answer to all of our questions.
That being the case, sorry, did I cut you off there?
Yeah, we have observations. I mean, this goes back to what science is. Science isn't about proving things; it's about observing reality and guessing how it works. I mean, that's essentially what science does. And we guess, and then we test those guesses over and over again, and the best guess float to the top.
And the reason we're confident this space-time is a thing, or at least it's a manifestation of something else that's a thing, but it's very close to what's going on because it makes predictions. This idea of a curved space in a 4D world makes a number of predictions that we can actually test. So, for instance, the bending of light around the sun in 1919, Eddington measured the bending, and it's different from the Newtonian result. It means it's by a factor of 2, and he found that the bending of the light around the sun during the eclipse in 1919 agreed with Einstein's prediction. Similarly, the orbit of Mercury behaves in a way that is explained by the space-time model. Similarly, with
extreme quantifiable precision.
Exactly, and also the speed, gravity travels at a particular speed is also predicted by the space-time. All these things Newton's work does not predict. So these are real-world things. It's not like we're guessing at something and then saying, "Oh, well, it could be something else." No, it makes predictions. It has utility.
To any detractor of general relativity, I would like them to explain to me what gravitational lensing is. What is that? Right? I mean. Yeah. I don't understand what that could possibly be other than the path of light traveling around massive objects.
Yeah, I would highly suggest not proposing open questions to them because they'll just say they're angels, and then they'll show you some. They'll show you.
They won't say they're green pixies, though, right?
Pictures of stars. They'll send you some out of focus pictures of stars and say, "See, this is what Jupiter really looks like."
Well, no, or there's like every single image through a telescope is fake. all of
they'll
space.
say that. They'll say
Which
they
is-
don't have any problem saying
Well, if we're being honest, I don't. How can you counter that? You know what I mean? You can't really. I mean,
that. Yeah.
There was one famous flat earther who suggested that all the telescopes that have been sold have actually got some electronic processing in them to emulate a spherical world and the stars.
Can I get us back on point real quick? Al Gate, the questions that you're proposing are, what is gravity? What is space-time? What is light? What is mass? These are names that we give phenomena in the world. That's all there is to it. We have a collection of observations that we know are factual. Every time we look at something, it does this, and we give it a name. And so it's actually backwards from, like, the way you're proposing the question is actually backwards from what's actually happening. What's actually happening is we see these sets of observations. We don't know what causes them or why. We give it a name, and then we start proposing ideas of how it could be working under the hood. And then we start testing those ideas.
Excellent point. But that is part of the problem with the miscommunication, is that people throw these terms around, but never really, if you can't show some kind of understanding behind these terms that you're throwing around, I think that's where you lose ground, when you're just communicating in general, or obviously when you're dealing with people who just want to start a semantic fight with you, whatever. But it's
here's the problem
it's
that
a
you run
bugbear
into with
that
Flat
people
Earth.
will use certain terminology and just kind of, they think they've just got the right to use it, but somebody else has come up with the term, somebody has come up with the physics behind it, whatever. And if you're using it, I think you should have some understanding of it. I'm not saying you want to be, everybody has to be a theoretical physicist. I don't mean it that way, but you have to have some general grasp of it, or why should you be communicating that concept to somebody else if you don't even really know what it is you're talking about? You know what I mean?
Well, here's the problem that we run into with the flat Earth, and Nathan Oakley is famous for this one. How do you know that space is real? Well, we've been there. Oh, you personally have been there because you said we. It's a different definition of the term we. We are talking on this panel. We as humans have been to the moon. It's the same term, but different meanings.
Yeah,
and that's the problem you run into with these guys.
They do go out their way just to try and get little gotchas, and they've got their own rules. It's all double standards. They'll use that argument when it suits them to get them out of a corner, essentially, but they'll immediately turn around and say, well, we know the Earth is flat, and we know the Michelson-Morley proved ether or some nonsense like that.
That one makes me insane. Like, someone made up that the Michelson-Morley experiment is the opposite of what it was, and then they all just repeat it. It's like, oh my God, you have no idea what that experiment was. You're literally saying it's the opposite of what it was. It drives me crazy.
The other problem is the second law of thermodynamics is volatile, and they misapply it regularly. But even though the second law of thermodynamics is their go-to science, they don't accept gravity.
I challenge them to state the second law of thermodynamics using Google as a reference, and they can't do it. it's remarkable. Yeah.
I like to ask, where does it say container in the second law?
Yeah. No, it's so far above their comprehension of thermodynamics.
Yeah, and this getting back to forces, actually, this idea, the second law of thermodynamics, they say that everything must be subjected to it. But then how come that we see an ordered world around us? We see solids and things that don't sort of distribute into a heterogeneous mass. These things are being held together. How are they resisting the second law of thermodynamics? And of course, it's forces.
Yeah.
Forces are holding bricks together, houses together, trees together, us together. Forces. And of course, it's the same force of gravity that keeps our atmosphere on, supposedly in their eye, in violating the second law of thermodynamics. It's old forces do the business of fighting against the second law of thermodynamics and providing us stuffing energy into the system. You can locally violate the second law of thermodynamics, providing overall you don't. And so when it can be, if you include this, we've got this huge
the thing that drives me insane is that they talk about George Musser like he is the god of science. And if he says Einstein broke the law or the wand of Newton, okay, well, that's gospel. And that means exactly what it says. What did George Musser do his doctoral thesis on? The atmosphere of Venus, a spherical planet with a contained atmosphere next to a vacuum. They seem to have forgotten about that.
Well, he did actually in his art. The reason, of course, he's become infamous or famous in our vote because he did that interview with a hangout in our community. But he did sort of contradict, and I say he mentioned that gravity is not a force, but then he said later on you must consider it a force, and then he also talked about the gravitational attraction. Now, an attraction to me means a force. It's almost like he's using a synonym. He didn't want to use the word force, even though the word attraction implicitly means a force. And then later on, as I say, he then said you must treat it as a force in equations. So he did sort of contradict, and this is what I was saying earlier. We must get physicists to stop saying gravity isn't a force in our world. That's what my earlier point.
I would second that.
It was a poor interview that left it way too open. That could have been tied up neatly in a package, and it wasn't because it wandered a little bit. That was the unfortunate thing about that interview.
Well, that's why I'm hoping he's agreed to give me an interview, a hangout that I'm hoping to do in the next few weeks, in which I will specifically put him saying, look, George, I know you sort of contradict yourself. I can quote the 2 bits where it says you must treat it as a force and it's not a force. I asked him, George, I know you're thinking of the 4D world again, but in our 3D world, could you please stop saying gravity isn't a force? So I will be pinning him down on that, hopefully, Bob, in the next couple of weeks.
Again, Rumpus, 4D?
3D are 3 dimensions and one at a time.
So, this comes back to
space-time. Space-time's a 4D world.
Space-time, but I thought it was a fabric. So
right. I mean, okay. Well, the thing.
The fabric of space technically a 3D world.
Well, no, that's the point. This is the point. This our 4D. I mean, this is the reason where gravity is like in this 4D world. I mean, centrifugal force, for instance, when you're in a car, it also depends. In our 2D, in our 3D world, we have. It depends on reference frame. So, for instance, if you're on a lift and you are falling in the lift and you then try and weigh something in the lift, you will find that it weighs nothing. So that reference frame, the force of gravity disappears. And so you can see there that it's the reference frame that determines whether you can perceive gravity or not. Now, it's a bit different when you have a 4D world. It's not quite a change of reference frame, as I've been pulled up recently by George Nathiuk. It's a projection, but it's a similar sort of concept. The idea, it depends where your reference frame is, and in that there's a like a centrifugal force, and in the when you're going around the car, we call centrifugal force an apparent force, because if you're in the car, it seems as though you're being flung out, but there are no forces occurring. It's actually your own inertia. You're just trying to go on a straight line, and the car's trying to do a bend, and you feel as though you're being flung out to the car, but you're not. And that's why it's called an inertial force, and that's why gravity is called an inertial force, because objects are moving through the 4D space-time in a straight line. This 4D world where time is a dimension. So we might think we're just sitting still, but in the 4D world, space-time, you're moving along. You're actually moving in this 4D world because time is a dimension. You're traveling along in a straight line in time, even if you're stationary. And it's the fact you're trying to follow that straight line in the 4D world, and then it gets curved by mass, that then gives you the appearance, this inertial force of gravity in our 3D world. So it's like centrifugal force. It's like as an apparent force. And that's why gravity is actually technically called an inertial force or an apparent force. And then some people will say it's not really a force, but it is in effect because it manifests itself as accelerating masses. Is that too complicated, Cal?
Agree or add or whatever to what Rumpus as you say?
I like that explanation. I think it's simple enough for people to understand, to say that we're just moving through it at a fixed rate, and that if you can imagine there's some sort of topology in there, and that's what mass is, maybe, if that helps. I don't know.
Yes, the topology is a good way. Yeah, the curvature. Yeah, good point.
Rumpus, it did clear up something that I had a question on. Talking about objects not really falling; they're just following lines in space-time.
Geodesics, they're called.
It cleared something up in my mind. But the problem that you're running into is that most of us, well, all of us on this panel, have the educational background to be able to at least look at a problem. And that is an issue that we run into with Flat Earth. Again,
I agree with you completely.
Don't understand why a book falls from your hand to the floor.
I agree with you 100%, Bob, and that's what I'm saying. But unfortunately, we've got to deal with flat earthers who've researched this and said, look, I'm finding all these physicists saying it's not a force. And that's why we have to use the argument I said earlier, right? You've got this 4D world with all this complicated theoretical physics, and it projects itself as a force in our world, and we call it a genuine force, just like in the lift, you can move the reference frame, but in our projection, it behaves exactly like any other fundamental force. So you've got to get this idea, simple concept, 4D world, where all this bending's going on. We are a manifestations projection of that 4D world where it manifests itself as a force. And George Musser shouldn't be saying it's not a force in our 3D world, but he can start talking whenever he likes about what it's doing in the 4D space-time world.
The problem that we're running into is they cherry pick individual scientific papers and distort the meaning of those papers. I did that with Quantum Eraser the other day. I located every paper that he cited that said gravity wasn't a force. And 2 paragraphs later, almost universally, it said, but in our world, it acts like a force. It reverts to Newtonian physics.
You did good work there, Bob, actually. I thought it was really excellent when you found that Quantum Eraser made that quote from something which said gravity is not, and it said not brackets, just a force, and he removed the brackets on just. Saying into
no, he removed the just.
That was great. So well researched there, Bob.
If I can try and bring us back on track to where we were going.
Well, you were saying my explanation was too complicated, weren't you? You were basically saying what I was saying was too complicated.
I don't want to belabor any individual point, but your description of 4D space-time, frankly, does not make any particular sense to me. I can understand the concept of inertial forces and things like that, but it feels like it's an addition of something that isn't necessary to say that there's an extra dimension in time, because when you're talking about something travelling in a straight line,
but it has utility.
That can happen in 3D space. So,
but Al, the point is it has
aspect of time.
But it has utility. The point is, it's not like we're making this up for a giggle. It makes predictions about the behavior of light going around bodies, the gravitational lensing. It makes predictions about the orbit of Mercury. It makes predictions about the way light behaves in terms of going away masses. It makes predictions about the speed of the force, this force of gravity. So it's not like we're doing this for giggles. And
no, that's not what I'm saying. It's the way of conveying it that I don't think makes any special sense. But what the idea that we use the equations and whatever to predict motions of planets and whatever, that's fine, because in essence you're adding in an extra factor to your calculations to adjust. So you've got your standard Newtonian, if you like, and then you're effectively adding in some curvature to compensate. In a very simplified way, I'm saying, right? Like you're adding in an element that helps better predict the motion through curved space, right? That's
Rumpus
the simplified way that I'm.
I don't think that's accurate,
if that's fine. If you want to correct me, that's fine. But what I'm saying is I can look at it from that point of view where you've got these predictive capabilities, but the description to actually explain what you mean by that, by time as a dimension and how it affects things, I don't think is adequate, if that makes sense. But sorry,
Rumpus
Dave.
is trying to make a statement to people that have a basic understanding of what he's talking about.
Well, as I said, the trouble is we've got people who are stupid who are finding these quotes, and we've got to say, we can't just ignore it. We've got to say, okay, the reason they're saying these sorts of things is because there's this 4D world out there, and we're a projection of it. And Professor Dave perhaps might be able to articulate. If you're saying that I can't articulate this very in a comprehensive way, perhaps Professor Dave can describe what I've just described perhaps more clearly.
I think you're doing a great job. I would agree that no flat earther will listen to more than 2 words of what you. It's not going to happen. I think what the points that we made earlier about just stressing, look, F equals ma. That's all there is to it. If something's accelerating, there's a force being applied to it. End of story, right? And just let, not play their game of quote mining, of here's something that Tesla said, and here's something that blah, blah, blah. I'm not going to play your game. If there's an acceleration, there's a force. You've got
to tackle their claim that they've got scientific citations that say it's not a force. You can't just ignore that claim. You've got to tackle it head on.
My typical response is that they're not qualified to comment on theoretical physics.
Okay.
Yeah, but if you look into those scientific sources, that's not what they say.
Right, that too.
And that's the problem. You have to read the whole damn paper.
Mm-hmm.
You know, you can't just pick one part and then have it and say it says one thing when the next sentence contradicts that. You know, here's the problem that you run into with flat Earth. Everybody on this panel knows exactly what Musser was saying when he said Einstein broke the wand of Newton. It's a very simple concept.
But the trouble is, he also said gravity is not a force.
Very simple third grade terms. Yet they persist in saying it because it suits their narrative. The problem is you're dealing with a narrative. You're not dealing with facts or reason or education. These are not stupid people. They have a narrative that they have to back up.
Yeah.
Right. So jump in here. As I say, I was actually trying to get back on track a bit and not go on too much about the whole 4D thing. Rumpus, you started this a little bit. You mentioned some things, but can you guys give us some examples of how Einstein's theories have been confirmed?
Right. Okay. Yes, I think there are 3 or 4 main confirmations of it. One was in 1919. I mean, he proposed general. I mean, in 1905 he proposed special relativity, which just dealt with constant velocity, and then he spent the next 10 years trying to account for gravity and acceleration. And then he had a revelation at one point, suddenly realizing that they were the same thing. And so in 1916, he managed to equate gravity exactly with acceleration. And then he made some predictions in his paper about the bending of light and someone's got a phone going. And in 1919, Arthur Eddington was then, with an eclipse, we were able to see that stars that were behind because of course, if you need to have the light passing by a massive body. And so that's the sun is obviously one that's near us that's going to do it. But unfortunately, if you look at that, you can't see we need to see the light from something behind the sun arriving at us. But unfortunately, the sun is rather bright. So the only time you can actually check what's going on, and as a star, the line of sight of a star goes near the sun, obviously it's all very bright. So it's the only time you got that is with an eclipse to obscure the sun. You can then see that the star moves as the sun gets close to it. Very close, the star moves, and there was a prediction about what that should be in Newtonian form. And then Einstein said, no, it's going to be twice as much. And Arthur Eddington, there must be there's some dispute about the accuracy of his measurements, but fundamentally people do agree that it happened. Then showed that what was happened, that the stars moved very slightly as the sun came close to them, or actually the eclipse with the sun behind it. They could see the stars moved, and they moved in accordance with Einstein's prediction, which all had to do with this. Which all around these field equations of a curved geometry. And then other predictions, like the orbit of Mercury, they spotted that was not quite agreeing with Newtonian maths, and it was changing its orbit very slightly. It wasn't quite arriving in the same spot. I can't remember, it's a factor of 1,000 or something.
Perihelion precession, the closest point that was shifting, right? That's
right, the perihelion, yeah. So, in other words, it's got an elliptical orbit, and the elliptical orbit was rotating slightly around the sun, and it was going more. It was not conforming to the Newtonian thing, and it was moving. And yet again, general theory of relativity made a prediction about what this should do, and it did it. And
using this model, this is what we should see, and that's what we see. I mean, with precision. So it's really undeniable. You know?
Absolutely.
So the eclipse is a very well known example. But I'm also looking for any other examples you can give. I think you've got things like, I forget the name, is it Hypho-Keating or something like that? It was the CCM clock thing and for time dilation.
I keep harping on this.
But anything you can think of that.
If you want a modern one, ask anybody who programs the clocks on any satellite. They all have correction factors that account for time dilation. Why?
Yeah. And so, for instance, when you have something orbiting the satellites, the GPS satellites going around the Earth, there are 2 factors affecting them. So, if you measure time at the top of the Eiffel Tower and the bottom of the Eiffel Tower, they're different. Again, prediction of general theory of relativity. And those satellites that go around the Earth, providing us with GPS, they have to make 2 accounts. One is the fact they're going quite quickly, which means that special relativity is affecting the time they're experiencing, and they're also being affected by the fact they're near the Earth and they're a different height away from the Earth. So the concentration of the gravitational field is of a different density on the surface of the Earth than it is up there, which means that time is behaving differently as a result of general relativity. So you've got two factors to deal with. And again,
with power, it's negligible, but with a satellite, if you didn't correct for it, it wouldn't work. So
exactly. I mean, I can't remember how far. If you didn't make a correction, I think you're out by a mile or something.
Like seconds, maybe seconds per day, or so. I don't even know. Maybe more. I have no idea. Like, not negligible.
Yeah, exactly. And the effect on GPS would be miles. The effect. So you absolutely. And in fact, I believe when they first put it up there, they actually had an option for not including general relativity and including it and special relativity, all the relativities, and they obviously. I don't know quite why they put them there, given the fact that established with atomic clocks that, even on, say, going to the top of the Eiffel Tower, you can establish there's a change in the way time progresses. And they did then switch it on and off and obviously confirm that these satellites did show that the effects of special relativity and general relativity were confirmed. And that's what we use now.
Right, so again, another sort of familiar example, but obviously in order to get to the point where we're launching satellites and allowing for time dilation stuff like that, things had to happen on the ground to test the theory before we went ahead with that kind of technology. I know, obviously, as I say, we've already mentioned some of the atomic clock stuff. Is there any other things that you're aware of, or it doesn't even necessarily need to be something preceding satellites, but just anything that's been done?
Yeah. Okay. The change of frequency of light.
Satellites were actually launched before they took that into account, didn't they? The first generation. Pretty sure that was true.
Yeah, they had to fix the GPS that were already in orbit.
That's right. They actually didn't account for it at first, and then they are having problems, and they're trying to figure out why, and they determined that it was because of relativity.
Mm-hmm.
The other extra thing was the change of frequency as light leaves a gravitational body. It changes in frequency, so you can actually see. There have been experiments done on the frequency of light changing as it changes in altitude. It's a very small effect, but you can measure it. So that's yet another general relativity effect that is measurable. You can do experiments on it.
Right. See, it's just one of the reason I'm asking this. Obviously, a lot of people like to question the whole relativity thing because, especially in flat Earth, they think it's all equations and nothing practical. And the other reason is something that's often quoted about these theories is that it's one of the most rigorously tested theories that we've got. And so if you can only come up with like two examples of how it's been tested, that I don't think that jives very well when you're saying it's been very, very well tested, but we've only done this. You know what I mean?
Can I comment on this, Al?
Yeah, I know. We could all Google. I'm just wondering if we between us, other things. That's all.
Yeah, can I comment on this real quick?
Yeah, please.
So I think it's kind of short-sighted of us to think that showing them a model that actually predicts reality is influential to them, because we have very simple examples of that, whether it be the Eclipse GPS or even the Lake Pontchartrain Bridge, where we literally have a geometric 3D model in 3D software that shows what it should look like on a globe, and we have the photographs that show it, and they just deny it. I mean, they just simply hand wave it away as,
refraction
whatever.
Or something.
Yeah, something else, even though the model matches exactly with the photographs and exactly with the GPS profiles. They just hand wave it away, So models that make predictions, while they're influential to rational people, they already have a preconceived conclusion, and anything that gets in the way of that, they just hand wave away. That's where we are right now.
Yeah, I agree with that. Obviously, I'm well aware of the people that we interact with every day in this community are famous for it. But one of the reasons why I think it's important for you to provide the kind of observations you do, and I do what I can, etc. I've always said, is you always have to allow for the people you don't know who are getting dragged into it, the people who are watching from the sidelines, the people who might listen to reason and look into the information and so on. So although the people we think of, the names that we know, they're literally just going to ignore everything you say. It's still important to have the information if you're going to be sitting here, attempting to provide information to people that are looking into flat Earth. Then you have to allow for the people that will actually listen. You know what I mean?
Yeah, I agree with that. I think that's why we all produce content, because we're actually going after that audience, not the actual flat earthers.
Yeah, exactly.
Jesse's making a good point in the chat that surveyors measure curvature every day, like over the course of just a few hundred meters.
Yeah, I mean, if you want, just you can just measure the horizontal. If you have a theodolite measuring what looks down, and you can see the two. I think it's over even just 600 meters. The angle of down is different. It's not straight down. Just by a simple measuring of what the vector to down changes over the distance of 600 meters, that you can relatively easily, with new technology, measure, and so therefore it can't be flat, or at least this direction, the vector to gravity, is not is angled.
Right, let's see. Well, I was talking about things that have been done in terms of measuring effects and backing up the theories and so on. And one of the things I had listed to mention was LIGO, which is in your neck of the woods, isn't it, Soundly?
Yep, 15 minutes from my house.
Wow.
So obviously there's been some discussion about that, about them, detecting gravitational waves, and there's some controversy over whether they really did it and so on, blah, blah, blah. What's your take on all that stuff?
Well, can I make a side point here, which is often overlooked about LIGO, which is that it's a 4-kilometer vacuum tube that's shooting a laser down it. And if the Earth were flat, they wouldn't have to account for Earth curvature whenever they shoot that laser, but they do. They do have to account for Earth curvature, and in my opinion, it's the best laser experiment ever invented.
What do you mean? What do you mean they have to account for it?
They have to account for the Earth curvature by
when they built
whenever they built it. When they built it, they had to account for it. They don't have to. Exactly. The tube is straight, but the Earth is curved, so the actual height on both ends of the tube is higher than in the middle.
Yes, that's right. So only when they built it, they don't. In the actual conducting the experiment, they don't have to account for it.
Exactly. But that, to me, is an interesting side note that, all laser experiments that are done by flat earthers and globe earthers alike are completely irrelevant compared to LIGO, which is the ultimate experiment. It's a 4-kilometer long vacuum tube. No atmosphere to deal with. I mean, there it is. There's your answer. Game over. They'll just hand wave it away, because the Illuminati space lizards own it. But anyway, as far as LIGO goes, you have 2 separate stations, and there's people in the chat that are even on our side that would disagree with me on this, but we have 2 separate stations that capture the same signal. I mean, I don't know how else to explain that other than there's some phenomena they're both measuring.
Anybody else want to weigh in on it? Anyone?
Well, I can. The other one, Virgo. There's a list. I mean, you just on Wikipedia has a very nice list of all the observations that they've made, and the confirmation that one received it and the other received it is fantastic. And as Rumpus was about to say, there's another one coming online too to give us yet another confirmation. The other part of the confirmation is that there were not just gravitational wave measurements that coincided, but other things, optical measurements and radio frequency measurements identifying these different events that happened. And at the same time, or very slightly offset, they see the gravitational waves.
Yeah, that's a great point. Actually, they got. I think with the only 2, you can't define within about 10 or 15 degrees where the things came from. But a third one came online, which when the neutron star collision happened, I think about 6 months or something after the first one, and they were able to pin it down quite closely as to where it come from. And so they went to a telescope and said, what had happened over there, that particular point at the same time, and what did they find? There was a very slight flash. So they actually were able to correlate the optical with the gravitational observatory, if you like, and bring them together. And yes, and then making that thing flat was an incredible task, because I keep on having to deal with flat earthers saying, how do you build something flat? And people say, well, okay, can't you just use a laser? No, it's subject to refraction. It's actually very difficult to build something that's straight. You can't use lasers because they're bent by refraction, and so I'm not quite sure how they actually did it with the LIGO thing. I think Jesse was a surveyor. I think there are ways of even with GPS. Well, you can, if you assume the GPS is valid, of course you can do. But something like that, that's not accurate enough, I think, for what the LIGO required. But it's actually a really tricky task. So,
yeah, they did use GPS. It was high precision GPS.
Oh, that's true. Of course, yes. As Jesse's pointed out, in fact, you can get millimeter precision on some of the high quality GPS. Yeah, that's right. So, but it's actually very difficult to do using optically because this goddamn refraction thing causes the light to bend by about 15 to 20% of movement in. So if you see something a distance away, it's actually being bent by 15 or 20% of the angle of a bending of where its position is optically. It's actually 15 to 20% moved as a result of refraction. So it's actually very tricky to build straight things unless you do things like GPS, which obviously, even radio waves are bent as well by refraction. It's a very tricky thing to build long straight things.
Does everybody agree that they detected gravitational waves, or do you have different opinions on it? What's the story there?
Yeah, I believe they did.
Yeah, I trust theoretical physicists to say,
Yeah, they detected them at LIGO, I believe.
So I think this leads to a rather obvious question when it comes to the whole force versus space-time discussion is, what are they actually detecting? What is a gravitational wave if a force isn't involved?
Well, it's the bending of space-time. It very, very slightly bends, and the amount of energy required to that is enormous. And I think they were saying when those two black holes came together, it was something like the energy released was something like several galaxies worth of the solar visual light output, and it's just this strange stretching of space-time, this fabric thing. So again, it's another prediction. I suppose that's true. That's one thing we didn't mention. There's another prediction of general relativity, that this space-time exists, and he predicted that there would be this bending of space-time, and that's why we've been looking for it. We've spent billions of pounds on it. It's only, after they spent decades looking for this goddamn bending of space-time that was predicted by general relativity, and it's only a couple of years ago they actually found it. So they were incredibly confident in it. Again, this talked about the experimental method. We didn't have a phenomenon, but we had a prediction of something existing, and then we went looking for it. We did not start off with this childlike idea of how science works. You start off with a phenomenon. Same with the Higgs boson. We didn't have a phenomenon that we were looking at, and then we have a hypothesis. We had the idea that something existed first, and then we went looking for it. And this fabric moving out. So it's another example of this fabric idea that supposedly is theoretical, but we seem to have experimental and real world utility in this concept.
Right, I wasn't actually going this way with it, but just because of the way things are going, I may as well ask, because I know some people will be thinking it. If we're talking about effectively a medium in the vacuum of space, things traveling as waves and so on, what is the differentiation between that occurring and the existence of something like the ether, would you say? I know the ether initially was really more related to the transportation of light itself, but just some people are going to work it back that way, that there is effectively a medium for energy or whatever to pass through.
I have seen that several times. Some flat earthers or others have said that they just renamed ether as space-time. It doesn't quite match because the previous version of ether was about light moving, not about gravity moving. But I guess you have a little bit of a point that it's some something that's traveling over some medium. But
is there drag in space-time?
Yeah.
Yes, there is. It's actually called frame dragging, which actually is another prediction of general relativity, that the idea of the Earth as it rotates actually rotates a bit of space with it, and that's actually been measured as well. So that's another prediction. We've got about 5 on the go now.
Well, maybe they have a point. I don't know. My understanding is ether doesn't exist.
It doesn't, but what I was talking about was space-time being dragged around. It's called frame dragging.
Well, I understand that, but one of the big things about, the Michelson-Morley, for example, they were looking for the ether wind and having it affect light by drag, and they didn't find it. That's why the Michelson-Morley experiment was important. But to say that ether and space-time are the same thing, you would expect a space-time wind, and we don't see anything like that. At least not to my knowledge and my limited understanding of space-time.
when we do actually in space-time, there's this very strange thing I don't understand at all called frame dragging, which is a sort of like a draggy thing. It's almost like the analogous with the ether, because there was this idea that to try and explain the Michelson, perhaps Professor David knows more about this than I do, but there was a suggestion of an explanation for the failure of the Michelson-Morley to find the movement was that the ether was actually being dragged around by the Earth, and therefore you didn't get the effect they were looking for.
Well, they were looking for the idea was that any wave needs a medium within which to propagate, and therefore including light, and that's what they were looking for. They didn't find the results were what set up the development of special relativity. They found no discrepancy in the speed of light, regardless of how they were measuring it. So, but I think the problem here is like flat earthers trying to conflate the search for Michelson and Morley's ether with something like space-time. You're just convoluting the problem by taking a thing that we know doesn't exist and putting that on top of a thing that it sounds similar but is a different thing. You know what I mean? You look for a thing and it wasn't there, and now you're looking for something else and you're saying it is there. It's like, yeah, it's a different thing. Like, what are you talking about? Like,
Absolutely right.
Yeah.
So let me think. So the other aspect that I mentioned at the beginning was the problem, if you like, of marrying up the concept of gravity that we have with things that happen at different scales. So we've got the quantum, and then we've got very, very large. I suppose I might as well do this. One of the things that keeps getting brought up by one of the trolls, Gleam, the galaxy rotation curve problem. Anybody get any information on that?
He's talking about dark matter, isn't he? Yeah.
I think that's like the solution or whatever, but what I mean is, do you have any kind of input on what the actual problem is and why gravity just isn't enough?
I'm familiar with it, but I don't want to monopolise this. And if Professor Dave or Toon or someone.
Well, gravity is enough, right? The dark matter doesn't do anything to gravity or how gravity works, right? It's just a way of solving a number of problems, galactic rotational velocities being just one of them, right? But yeah, I mean, flat earthers, actually, here's one thing that I really want to bring up, and one area that deserves a lot of criticism is science media, because they will report on things in a very sensationalist way. And so dark matter already has a really sexy name. And so when you get blog posts that kind of dress it up in another fantastic way, then you've got lay people, and especially flat earthers, thinking that they understand a concept like dark matter, which is absurd that they would think that they could possibly understand that, as they're not astrophysicists. And then they'll just say that it's ad hoc and it's just bullshit, and whatever. You're not an astrophysicist. Astrophysicists are in pretty wide agreement. I mean, there are outliers that think that we need a different model of gravity, but it looks really, really pretty firm that there's dark matter. Okay, we don't know what it is, but we're working on it. I don't know what else there is to say. Just to identify that there exists a frontier of science. There always will be something that we're trying to figure out. That doesn't make science invalid.
The reason we bring in, I don't know, perhaps Professor Dave wants to go about why we think dark matter exists. I've got a few points on that.
Yeah, I actually was prepping for a podcast episode on this, so I wrote some stuff down. Let's see. Yeah, galaxy. Rotational velocities. The distribution of rotational velocities of stars as you recede from the center of the galaxy doesn't quite match what we would expect given the distribution of mass. It's sort of like the velocity increases and then just sort of plateaus. I don't know exactly what the calculations are, but it would require like a certain, like a 6-to-1 ratio or something of dark matter. And
the reason we think it's not matter like black holes, there are several reasons why we think it's not black holes and stuff like that we can't see, that we know is dark.
This is submicroscopic black holes. That's one hypothesis of many. There are many.
I think Yes, that's right. There is a suggestion about that, actually.
Yeah.
And then they're suggesting there's been invalidated recently. I thought there was something against it.
I don't know. I'm not on the forefront. I'm not super on top of it. I mean, most of the hypotheses, most of the proposed hypothetical particles are things like WIMPs and machos. They're just non-baryonic matter, right? I think that people get really confused about this idea of dark matter. Why can't we see it? Well, why should you see it? Why do we see things? Because it interacts with light, right? Atomic matter interacts with light. Everybody remembers the Bohr model from general chemistry, right? The photon gets absorbed and then it gets re-emitted. If it doesn't do that, you can't see it. So if it's not baryonic matter, why we wouldn't see it? But
and when you say baryonic matter, you mean protons and neutrons, don't you?
Yeah, atoms, the stuff that atoms are made of. If it's not made of those parts, like what, one proposed thing is just there's a ton of different kinds of neutrinos or, just other particles, just different particles, that don't interact with light. I don't think it's that shocking an idea, really.
And the reason that we've got this deficit, we think there is this missing matter, because we know from the cosmic microwave background radiation how many neutrons and protons there are. There's a means, I won't go into it now, of saying, looking at what the cosmic microwave background radiation is telling us, and that gives us an upper limit on the number of protons and neutrons, which gives us a limit on the mass that is from baryonic matter. And then when we see things like when we add up the mass of the galaxies that we can see using their rotational information, we find there's a lot more out there than we can account for with baryonic matter. So therefore we have to then say, well, okay, we've got something else out there that's not baryonic matter that's accounting for all this stuff in galaxies. And so that's where we got there are other things as well.
Something about supernovae, the standard candles, something about that.
Yeah, and also something called the bullet galaxies, where there are two galaxies that have collided. And we can see from the image of where the collision, where most of the mass is, and where most of the light is coming from. We can see that the mass is not interacting with where the light is, and from that they've drawn that that there's a lot of dark matter there that's weakly interacting, which is the quality of dark matter.
One very convincing thing that supports this too is when you take what we propose is the ratio of dark matter to regular matter, and you use that value to run simulations of the development of the universe, you find that you actually need that ratio for the formation of early galaxy clusters and superclusters. In other words, without that dark matter there, we theorize anyway that galactic formation could not have gone the way that it did in the timeline that we understand for the history of the universe.
And that's absolutely correct. Exactly correct. It's absolutely critical to the formation of galaxies in the early universe. Yep, absolutely right. So then we've got loads and loads of good reasons. Not something I've made up. It's coming over many decades, and they go, where we've got these deficiencies, and then we're forced by observation to say, well, our only models only work, and we've got observations that show there's some extra mass that we're missing, and therefore we're forced to come no detection of this actual matter, but we know it's got mass. But unfortunately, the only thing it interacts with is other mass. And unfortunately, doing experiments with mass is very difficult. It's not something we can have in lots of mass in the lab. And you've got a black hole handy. It's one of the few things you can't manufacture more of or do more with. You will make it. You can't make mass, unfortunately. Well, you actually you can. Sorry, I lied about that. You can energy. You can actually make a bit of mass.
And honestly, the only reason the public fixates on this topic is because we named it something sexy like dark matter. That really is it. I mean, ever since, I don't know what the first thing was, but ever since maybe quarks or something, where physicists just decided that everything needs a fun and whimsical name, it's just progressed to the point where we have dark matter and dark energy, and the public just sort of goes, ooh, what's that? If we named it non-baryonic matter, no one would care. No one would be talking about it. It's really that simple. I mean, I love the fun acronyms and stuff, but maybe the physicists should stop doing that,
Oh, I think that's not going to stop. They love the idea now, I think.
I like it too, of course, but it's just, I have a real problem with science media, because you've got the sexy names, and then they present it in a sensationalist way, because we live in the era of clickbait. But it's really strongly affecting the way the public is consuming science, and in a very negative way, in my opinion.
Dark energy, dark. It's dark and it's energy. Oh, yeah. Darth Vader.
Yeah, yeah, pretty much. Yeah. take all the yeah.
I could carry on speaking, but I don't want to monopolise anything. I told by Al again.
I muted myself. Sorry. Can you hear us okay?
Yeah.
Oh yeah.
Yeah.
Right. So there was something I wanted to bring up, and I don't know if everybody will know what I mean. And I specifically, as I said, just the same as you guys, I've not went away and tried to look anything up to try and be a smart ass tonight or anything like that. But it's just something I kind of hazily remember from a couple of years ago. I think it might have been when they landed the probe on an asteroid. You know what I'm talking about?
Oh, the one with the ESA did the one. Yeah, the one that bounced around a bit. And then hid inside a hole, and then when the sun came round, and it only lasted. It bounced. It tried to dig itself, and it hid itself in the shadow, and it didn't really come active again.
Well, I don't know if I'm thinking of the right thing. I just
What looked like a duck. The asteroid looked like a duck.
I'm not sure that I'll explain I'll tell you the part that I remember, like reading about or whatever at the time, and I don't know if I'm citing the right thing here, but it was some asteroid or whatever, and when they basically got to it to land on it, test it, whatever it was they were doing, they were surprised to find that it had less mass than was expected. Due to the predictions, I assume based on its expected its gravity, if you like, they got a result that they were not expecting, and it was actually it had less mass. So I don't know if anybody knows what I'm talking about. It's been a while, and I'm sorry I don't have better details than that. But
you need to give us a name. I think it's the duck one you're thinking of, and it might be they decided it was slightly hollow or something, or at least made out of
something like that.
And that's why they couldn't drill into it. That's why they bounced. It wasn't substantial enough for them to dig into it or something.
Yeah, it's just that the thing about that was
set off the bomb, or
say that again. Sorry.
Was it after Bruce Willis set off the bomb, or was it?
Yeah, I don't think that one had less mass.
I'm not familiar with that precise aspect of that mission.
Yeah, as I say, I didn't go looking for it, which maybe I should have. It was just something I kind of hazily remember. But it was
I think it's the duck-shaped one you're thinking of.
If that's the case,
2 or 3 years
raises
ago.
that, just that little question mark over how well are we able to really know the mass of something. You know what I mean?
Mm-hmm. Mm-hmm.
Yeah, but it can have a different mass. I mean, just because it's got a volume doesn't mean to say that it's solid or it's not made of a low density material or high density material.
Right. Maybe it had to do with us misinterpreting its precise composition.
Yeah, exactly. So things are allowed to have different. They don't have to be specific. Obviously, if it behaved in a way, something that its mass would determine. If you could work out what forces were acting on it, and it wasn't, and it was responding in a particular way that suggested, like we were talking about inertial masses that respond to a force, and then somehow later on we had a different value for it. Now that would be a problem, but I'm not sure that's what happened.
Well, as I say, unfortunately, I don't have the full details. That would probably help, but I just. If that had been the way it went, if there was certain predictions made based on obviously its orbit or whatever, I assumed it had a certain amount of mass, blah blah blah. Then you get there and you find out that that's wrong. That would be a problem. You know what I mean?
Yeah, you don't want two different measurements of mass. But then the Rosetta, that was the Rosetta one, I think, with the rubber duck. Yeah, and it was the it was an ESA mission, I think, and it was it was 2014, 4 years ago. Comet, I'm looking now, Googling it. Comet 67P. God, there's some Russian names. I think that's the one you're thinking of. There's shaped like a duck, like a plastic duck. Do you don't remember that? I've got a shot. Okay, here we go. I've got a picture of it here. If it's the one that. Oops, let me go. In fact, I've even got an animation. In fact, I even got an animation of it. Here we go. I can share this.
Of course, you got an animation because it's all CGI.
Yeah, here we go. I'll share the thing.
Just while you're doing that, one of the other things I was wanting to kind of talk about. So, if you're going with the bending the space-time thing, and obviously we're looking at distant galaxies and so on, and we look at orbits, we're basing the predicted paths of planets around suns, etc. But how far of an influence? I don't know if you'll be able to answer this, but how far outside of a gravitational body will effectively the gravity well of that particular system extend? So, for example, our solar system, the sun, how far can something orbit the sun? Essentially, obviously, I'm assuming galaxies overall have much larger mass. So, in terms of how they would warp space time around them, they would have a much greater influence, etc. Anybody get any general way of going over that, or is it just numbers that you don't know?
I've got this thing, an animation here for you, Al, of this duck-shaped asteroid I think you're referring to. If you present me.
Yeah.
Can you see that? That's the...
It's a mild resemblance.
And there's some more high-res pictures of it, if you can see. This is, yeah, that's the one. That's a bit of a sharper one there. It's just, see if I...
Insofar as a rubber duck is also just two blobs, really.
Oh God, there we go. That's the right. So that's the.
I mean, how was flat Earther seriously called?
Yeah, it's all part of the making it accessible, isn't it? To make everything friendly, and it looks like a rubber duck. Yeah, and that's the one where they lodged. They tried to land in one spot, they missed slightly, bounced off it, tried to dig a hole, couldn't manage it. They had these little impact things to try to drill in, failed, bounced around, and then hid in a shadow. And of course, that wrecked its bloody solar panels, so they couldn't could only last for 48 hours or something.
Impressive that they even hit it.
Oh, that's right. That's right. They believed this. That's right. They believed it came together because it's got this rubber duck shape. They believe it was two things that came together, as this animation here is showing. And that's what possibly. Yeah, I think one part of it was low density material. Yeah, I can't. Yes. So I think this is the one you're thinking of, but obviously only you know, Al, what you were thinking of.
As I say, it's just something I vaguely remember. I know it's a couple of years ago, and it's just a little bit of information. Only part of it stayed in my head. You know what I mean? So I didn't go hunting for it before the stream, which I maybe should have. You know.
Sorry, I interrupted your question, by the way, Al. You were asking us all the question, weren't you? I interrupted.
I know
you.
I did say it. I was just saying that if it was a case of they were basing their the trajectory of their probe and so on, and where the path of that asteroid based on the understanding of how much mass it's got, how its gravity is, blah blah blah, and then you get there and it's got a lot less mass, then that would be a little bit of a question mark. You know what I mean? And then that
but how would they?
Sorry.
The same calculation they use to determine its mass would still apply at close range. So that's still good.
Well, you could see, presumably, what they. Here's a conjecture. If it was going past Jupiter or something, you could see how much its path moved, and if it moved by a certain amount, there was mass there. And then when you land, I think, as I remember, the descent stage, it went down by 1 meter per second. I think it was the final descent of the lander. And that's determined by the gravity, the mass of the thing. And obviously, if those two things were different, then you'd have a problem. But I don't recall any fuss about that, Al. So I think it's just a case of they thought that perhaps density was different from what it. I don't think there's an issue with some fundamental theoretical physics problem here. I think it was just a case of, it looks this particular density, and it wasn't because it's hollow or something.
Yeah, it's hard to predict that kind of stuff.
Yeah. I mean, density of asteroids are very different. There are the ones that are sort of iron ones, and then there are others that are more sort of rocky, and they're very different densities.
Mm-hmm.
Yeah, that's fine. I just thought it was an interesting little point to raise, and bearing in mind I'm devil's advocate, so. What else? So, going the other way, quantum scale. So there's maybe Dave, you can kind of give us an idea on this. Is like there's a general sort of effort to try and get some kind of unified theory that lets gravity kind of work in every scale and whatever. So,
yeah, I mean, I can give you the ultra basic. I mean, with the advent of quantum physics, Richard Feynman developed quantum physics that way. Explaining fundamental forces no longer as field forces, but rather as being mediated by particles. So with quantum electrodynamics now, instead of thinking of an electromagnetic field, we're thinking of two electrons emitting a virtual photon, which pings off each other and they repel. So we're talking about particle exchange now as being able to explain the electromagnetic force. So that's quantum electrodynamics. Then quantum chromodynamics did the same thing for the strong nuclear force. And so theoretical physicists are looking to do the same thing with gravity, and the completely hypothetical particle that would mediate quantum gravity would be the graviton. I don't know where they are at with it. I don't know how, I don't know about it. That's the word on the street in the theoretical physics community. So.
Okay. Rumpus, you got any interest in that side of things?
Sorry, I had to go away there. Yes, we're talking about. Sorry, unfortunately, I missed what Professor Dave said. But no doubt. So I probably.
I just mentioned that what quantum electrodynamics did, and then we had quantum chromodynamics for strong nuclear force, and there is essentially trying to do the same thing for gravity. Find a quantum field theory for gravity, such that it was mediated by a quantum particle.
Yeah, indeed. I'm utterly confused by this. I was asking Professor Dave earlier about these gravitons because, in fact, one of my questions to George Musso was when he's hoping to talk to him is how can we have this wonderfully working curvature? Anything
right.
Seems to make all these wonderful predictions, and then suddenly we've got, which doesn't involve. It's not it means it's not a fundamental force. It's not a force in that 4D world at all. And suddenly we're saying we've got to have these gravitons, this quantum stuff, all happening, just like as Professor said about the.
To me as well, but I'm not in the habit of arguing with theoretical physicists. So.
Yeah, not a good idea, is it? So,
I don't understand the math, behind it. So it's.
Yeah. I never got the grips.
Where they turn up,
Are you familiar with quantum chromodynamics then?
I mean, vaguely. I have a 4-minute tutorial on it where.
Right, do you? Okay, I could probably do.
But I basically name the particles, and this is the most basic level of these. In my modern physics series, I basically just try to convey the concept of explaining these fundamental. Quantum field. It's not.
Yeah, because as I understand it, we don't fully understand the forces that the quantum chromodynamics do. Do we actually have a full-blown equation that works for the forces between gluons? Not force between gluons.
I think so, because I think that there are unified theories that work and are predictive.
Right. Okay.
But we have not yet. And also because we've merged all of those into the so-called electroweak force, that we can. That would just be electromagnetism.
Yeah, that's right. The strong nuclear force is outside that, isn't it? Yeah.
Right. Yeah, strong nuclear. That would require a unified theory. I think that the way that we verify these is by predicting particles and then just using a particle accelerator and see what we see. So I don't know exactly what the highest energy or how far back we've probed to the early picosecond of the universe. But apparently it's just a matter of getting a bigger and bigger particle accelerator, and we'll get them all. So
because quantum chromodynamics is something I just scares me. Just even though it just seems so incredibly theoretical that you have to invent special maths for it and things.
I have great ambition to one day understand it. I'd like to learn enough math. If I can get to a point where I can pull back away enough from the work and become sort of a student for a living, I will go and I'll learn all those maths and I'll learn all the physics and I'll learn all that stuff. But I'll make you better believe I'll make content about it, because there's not that much content on frontier physics that is intelligible, or deep at all. Right? It's usually just clickbait.
So my answer is. Yes, there's this strange thing where there seems to be this contradiction between this curvature stuff that seems to work wonderfully well. It doesn't require any. It's not that means that gravity. They talk about the 4 fundamental forces, but from this curvature business, it isn't one. So we talk about this unification that Stephen Hawking was talking about. This unification. We talk about this theory of everything, TOE, which is supposed to bring all these 4 fundamental forces together. That's as mentioned: the electroweak, the strong. Gravity and
electroweak is electromagnetic.
It's electroweak, and so those 4 coming together. Now we're fundamentally saying, well, actually, there's only 3, so we've done it almost. So it's really weird.
Yeah, I'm confused by it, but we'll see.
See, I think things like that are interesting for that reason. I know that for the people that we've been talking about, they would leap on stuff like that as a way to just deny everything, but I still think it is an important point. Like, how do you reconcile these 2 points of view, where you've got a system that doesn't require a force, and then another way of looking at it that brings you back to, well, we are looking for a force. And
we're still learning. My physics, one of my physics, I said we probably only know about 5% of what there is to know. Everything. So, if we've got this, we've had probably, we didn't know 100 years ago that you could change time. I mean, my God, it's just an amazing concept. The idea just by being at the top of the bottom of the Eiffel Tower, time is traveling at a different rate. I mean, I still find that absolutely
see
incredible.
Things like that again. So talking about effects on time, is it really an effect on time? Or is it really, when it everything boils right down to it, it's still a physical thing? So it's not really time itself. It's just that something is affecting the matter involved in some way. And so, just for talking sake, the frequency of vibration of some atom or something like that will change, if you like. It's a physical process sort of thing.
Yeah, it does change. I mean, if whatever measure you want to make of measuring time, in other words, have frequencies of light, or the way how quickly an atom wiggles around, or how long it lasts, which was the classical one. There were these God, I've forgotten their bloody name. Pions, I think, coming in. They only exist for something like 3 microseconds or something, and they're generated. Sorry. Muons, that's it, muons, yeah, get it right. Muons, and they were hitting the atmosphere and being generated in the upper atmosphere. And they don't have time, for their known lifetime, if they're stationary, is such and such. But when they're coming created at very fast speed at the top of the atmosphere, we know they shouldn't get to the surface, but yet they do. So every part of this thing indicates that time has changed.
That's replicated in a lab too. It's not only atmospheric observation.
Yeah.
We can in the lab look. They last. It shows this long. We send them going at speed. It lasted that long.
Yeah.
It matches the equation.
Yeah,
Time dilation.
It's as real as it can be, Al. Everything says it's absolutely 100% a real thing.
Yeah, this is one of the earliest things I remember hearing about was the changes in half-life of various particles. And would you suggest or agree with me even that maybe this still comes back to maybe the language that's used, similar to dark matter? When you say time dilation, I think it maybe invokes a certain concept in people's heads, and it maybe doesn't quite marry up with what's physically going on.
It does marry up.
Yeah, to dilate is to expand. So from the perspective of the frame of reference that is dilating, time has dilated, right?
It's changed.
No, what I'm getting at is to your average person, right, who hears that statement, time is like a concept. It's not a thing that you can manipulate. It's not.
But it is a thing you can manipulate.
You see what I'm saying?
But it is a thing you can manipulate. You can just travel faster. We know it. In every regard, it's a real change. It's not like we're putting in some numbers and just trying to compensate for something. No, it really is happening.
Yeah.
So maybe I missed something there. So my initial question was that is it really a change in some, in time, or
yes.
if it is just a physical change in the way things behave, and that in turn is what we perceive as time, is the motion, if you like, is really what we're looking at, because that's how we measure time. Obviously, is by applying standard increments.
By what mechanism could that kind of change affect the way an atom vibrates and how fast your heart beats and how long a particle takes to decay and every other, right? If it changes, it doesn't change everything that measures time. It changes time itself. That's how everything that measures time changes similarly, because time itself is flowing at a different rate, right? Any mechanical clock, any biological clock, any clock that is conceivable will demonstrate that that time is flowing at a different rate, right? That was demonstrated as early as putting the precision clocks, one on the ground, one in the plane, send it around the world. The one on the plane time went a little bit slower for that one.
Yeah, it's uniform, everything. Whatever you want to measure, if you want to regard that everything's suffering the same effect, then okay, but that's the world we live in, that's the universe we live in. The whole universe, if it's all changing in the physical, and it's not just physical, light as well. I mean, I suppose light is okay, and you can't change the speed of light. In fact,
Right,
yeah, so distances. I mean, that makes up for it by the distances change as well. This is how. Yes, you have time length contraction as well as the same result, because
the perceived lengths. Yeah.
Yes.
So let me simplify it, right? So let's say you have, I don't know, let me think, just say you take something very mechanical, like a ball bearing being pushed by a spring, and it'll have a predictable path, due to the energy stored in the spring, pushing the ball bearing or whatever when it's released, etc. And on the ground, it's obviously going to be more affected by the gravitational field than it would be if it's much further away from the Earth. So that the effects would change, and it's because of a direct physical effect of gravity upon that object. So what I'm saying is doesn't that dial down right down to everything, to every molecule, to every atom, to every electron, whatever, that actually makes up all the mass, and isn't that basically a universal effect upon everything that makes up each object?
I don't think I understand the question.
So what I'm saying is that, so if you look at it on a macro level, we understand that you've got a physical effect upon an object by gravity, right? And then if you reduce that effect, it changes how that object behaves. Why wouldn't that same essential principle apply to, for example, the spin of an electron or something like that? That although it's a very, 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 very tiny effect maybe at that level, there's still some effect. And so, depending on whether it's closer or further away from a gravitational field, it's either freer or more constrained in its movement, essentially. I know my words are very simplified here, but that's the idea, is to look at it the most simple, sort of straightforward way.
Well, you have to look at what is affected by gravity. The spin of a particle is not really correlated with its position in a gravitational field, or that wouldn't be my understanding. So maybe it's just a discussion of whether or not you regard the rate of the passage of time as a physical construct or not, which I don't really know.
Yeah, that's kind of what I'm getting at. Is it a physical thing? And it's really just about how everything, fundamentally behaves. And, the timing is really just a matter of essentially how everything moves. And
as a reduction,
how it moves within certain circumstances is going to change. And so by that change in rate of movement, you then get the different timings of everything, because obviously everything kind of comes in a sense to frequency and vibration. So
here's something you might want to consider just to confuse yourself. Absolutely. If you were a photon, how do you perceive the world given the fact that you're traveling at the speed of light and therefore you perceive no time?
Or space. No
yes,
time.
Or space, yes, because because the space contracts into nothing as well, the length contraction. So photons, as far as they're concerned, live infinitely long, or time never passes at all for them. Well, that's...
They're everywhere and nowhere. They're all never. They are God. Every photon is a little God.
Yeah, indeed. I can't cope with that one at all. So that's and of course, and then
that's just.
Well, imagine this. Also, if you want to think of this way Einstein actually determined special relativity in the first place, he was imagining he was traveling along a light beam at the same speed as then he started to move in. Or you want to think if you had a car that was going along the speed of light and it turned its headlights on, what would be the speed of the light coming out of the car? And you can use the Lorentz contraction to try and come to a combination which I won't go into, but it's and then of course you get problems about simultaneity, things like two events. There's some excellent videos on YouTube showing a train that's going along near the speed of light, and whether it's being trapped in a tunnel, whether one door is opening at the same time as another door, and everybody's perceiving everything happening in different orders. It gets very, very complicated.
Really, if there were no universal speed limit, causality could not be a thing, and we need causality for any logical coherence in a universe. So that's the way I see it. I mean, it is specifically that we need a universal speed limit that makes special relativity true, because we need for the speed of light to be the same in every in every reference frame. And so that's why time dilation and length contraction happen so that speed of light will be measured as.
Actually, Professor Dave, why we have to perceive time as being the same speed in all things, and why not the speed of sound or something that's twice the speed of light?
Oh, why is the speed of light the speed of light, the number that it is?
Well, we know it's a permit, but why? But why do we have to have this constant? I suppose it's the permittivity. Yes, in Maxwell's equation, obviously, give it why it's a particular speed. But okay, perhaps the question I'm asking is why is that speed? I suppose that's what makes a speed special. I suppose the fact that we. Okay, perhaps I'm answering my own question here. The fact that we measure these constants of the permittivity of the magnetic and the electrical permittivity and the magnetic permeability, you get a result which means that there's this. It comes up with this speed. So possibly, yes. Anyway, perhaps I'd like to develop that, Professor Dave.
Well, when you get into E&M, I get lost real fast. I don't know anything about it. But
I handed it over to you. Sorry about that. I handed it over to you. A little bomb there.
No, yeah, I don't know. I mean, but the concept of just, I mean, any other object, if you're the analogy I use in my relativity tutorials is if you are traveling 90 miles an hour on the well, some of you guys from the UK, so maybe kilometers, I don't know. But
we're miles an hour here as well.
Okay, so now 90 miles an hour, and then somebody passes you going 100 miles an hour. From your perspective, they're going 10 miles an hour, right, from your frame of reference. And so then so that's Galilean relativity, right? But then, then I show, but Einstein said that's not true for light. So, even if no matter what you measure light speed, as it is the fundamental constant of the universe, and the ramification of that is time dilation, right? If you're going very close to the speed of light and you still see light going same speed, you must be experiencing time differently than a person who is stationary relative to you, right? So yeah. And again, it's just if there were not a universal speed limit, causality can't be. I don't know. Sometimes I just like to think that the universe just like is at the simplest it can be,
But that's it. I haven't heard that before, actually. You're saying there has to be a speed limit, otherwise causality wouldn't work.
Right. And how can you have a coherent universe without causality?
But why is causality a necessary? Why is a fixed speed of light a necessary consequence of causality?
Because otherwise, effects would precede their causes.
Well, surely you could have something could be infinitely. I mean, if I do something A and it travels instantaneously, and somebody does something at B, that hasn't changed causality, has it? Or is it the fact that it's instantaneously having an effect, breaching causality at B?
Right. There are very elegant thought experiments that demonstrate this that are eluding me at the moment.
Right.
But they're out there. Yeah, if I had a minute, I would check it out. But yeah, definitely, it's worth Googling. Just sort of like a demonstration of how
because of course we do have instantaneous with the coupling of things, the EPR paradox and things, where we do believe that quantum physics says that if you do something over at A and it's been entangled with another particle that you've taken away over to B, you've got an instantaneous change. And it seems to be, I mean, this is even more weird than we're getting into quantum physics here, perhaps it's inappropriate, but it's an amazing concept that this. And Einstein, of course, never accepted this. The fact that you could be at A and you could be at the other side of the universe at B, and you do something to A, and that causes the particle at B to at least change. You might not be doing it in a controlled way, but it does change.
Right.
Of what
it gets worse than that.
Done over at
My
A.
understanding is that the jury's out on it. I don't like myself.
There was something that popped up in my feed the other day. Don't expect me to go into any detail on it, but it was temporal entanglement. And it's effectively, the kind of similar to the, the delayed choice quantum eraser, or just the quantum eraser, whatever. Same basic principle, but they had like a series of photons, and then controlled the order in which some were destroyed after they were split, and basically an entanglement formed between, a newer part of a pair and an older part of a pair, sort of thing.
That's right. That's it. This is the quantum entanglement. Yes.
And, it's not just straightforward entanglement though between matched pairs. It's one half of an old photon and one half of a new photon. It's two separate photons. You get what I'm saying?
Yes.
It's taking it to another level again.
Okay,
it's not just about the physicality of it; it's about the timing as well. So, You need to look into it. I only kind of glanced at the article.
Okay, I'll have a look at that.
But just look up temporal entanglement and it will come up.
Perhaps we have gone a bit deep here. Anyway,
No, I'm just saying, you guys are talking about stuff that confuses the shit out of you. Go for that. That will really
apparently we were confusing you earlier, and now we've moved into something to confuse you even more about a different subject. So
we're talking about things that are confusing to the physicists that are working on them, right? Of course, we're not going to, all we can do is report what their conclusions are if they have them. I'm not a physicist, I never will be, so I can explain basic physics, but when it comes to the frontier of the field, what can I do but report the consensus of those who are studying it? There's nothing more I can do,
You guys are well above my level.
Perhaps we've gone too far then. If Bob is having problems, then perhaps we're becoming irrelevant to Flatty. I don't know what this debate is. What is this debate about, actually? We're just talking about gravity, or is this the gravity for Flatties, or what, Al?
The thing is, what is gravity, I think, right?
Essentially, what is gravity? Where do you stand on it? Is there a consensus? Is it a force? Is it not a force? Is there a discrepancy in how we understand gravity, especially when we move across different scales and so on? So is it right for somebody to question it and say we don't know what it is when we're talking about in everyday life, or all that kind of stuff? So just a kind of general overview. Where do we stand on it? Do we agree? And ultimately, what's your kind of conclusion on what it is for now?
Is that a question we want to sum up or something? Is that because I think we've covered?
You could do. I mean, I think we've covered most of everything. Some of the things I would have maybe asked about were naturally covered. So.
Look. Can I say this real quick?
Yeah, go ahead.
We don't know what gravity is, like what the underlying mechanism is. We have no idea. We have a set of observations, and we have a model which we think explains it pretty well. But to assume that the model is in fact what reality is doing underneath the hood is a reification fallacy. We can't do that. We can't say that the model won't change and that there might be a better idea at some point in the future.
Science is provisional.
Yeah, and also from the flat Earth point of view, it's really a double-edged sword. On the one hand, they want to say that we don't know what shape the Earth is because science doesn't know stuff.
Right.
But then, on the other hand, they want to tell us, well, you should know this, you do know that, you say this categorically, and if it's science, it's set in stone, and it doesn't really work like that. I mean, I think a general sort of example of that is that ball lightning, which is a natural phenomenon that anybody can observe if they're lucky, obviously, is not truly understood. The mechanism behind that it's only been recently a kind of breakthrough in that, I think a couple of years back, which I think was by some scientists in China. The mechanism behind how ball lightning forms is not really properly understood, and that's something that's happening, every day essentially, if you like, somewhere on Earth, perhaps. A general sort of natural phenomenon.
My physics lecturer claimed we only knew 5% of what there is to know.
Mm.
We have to find a way to balance communicating the wonder of science and the thrill of figuring out what we don't know with being careful about projecting the idea that science is uncertain and we don't know anything and everything is, I would say, it's a very tight to I don't like anything that gives them ammunition to propose that, the idea, you guys don't know what gravity is. Well, yeah, I guess kind of, but we know way more than enough to explain to you what gravity is. Yep. And that should be, that's where I'm at with it.
Yeah, no, I think that's good. Yeah.
Yeah.
Right. So after all of this discussion, if I was to go back and ask you the original question, would anything change?
Not for me. I think I've stuck with all my original position, I think.
General relativity with being open to the idea of quantum gravity, whatever the hell that is, and however it may be explained to us at some point in the future. That's where I'm at.
Right, and obviously nobody in the panel has a problem with the concept of something manifesting as a force.
Yeah, I like that. That's so I don't like physicists because they want to talk about their lovely 4D space-time world, then saying gravity isn't a force when they seem to
it's not apparent force. Either call it a force or call it an apparent force. One of the two. Just that's it.
Yeah.
That's all you got.
Yeah, that is actually where I was going to go with what's it that causes hurricanes? Oh, to mind blank all of a sudden.
Coriolis?
Yeah, exactly. The Coriolis effect. That's an apparent force.
Yeah, exactly right, Stanley. Exactly
it's not an actual force, but you can see a force being applied to weather systems.
Yeah, in our reference frame, in the reference frame of the surface of the Earth, it behaves just like a force. Just like being in a gravity, if you're in a falling lift, suddenly gravity ceases to be a force. And in a centrifugal force case, there's no force there, but your inertial your movement, it makes it seem like, because the reference frame you've chosen to be a force. If you move the reference frame with the accelerations occurred, you can either create an acceleration or remove an acceleration. It's all about reference frames. So yes,
and force, etc. Yeah.
And if our reference frame is on the surface of the Earth, then the Coriolis force looks exactly like even an apparent force.
Agreed.
Well, if nobody else is, if you're happy to more or less tie it up now, I do have some questions that Tommy sent me. If you guys want to go ahead and try and answer any of these, you okay with that?
Go ahead.
Yeah, sorry, getting a bit of robot in there, so everybody hear me, yeah?
Mm-hmm.
Yep. You occasionally.
Yeah, I think it's starting to go a bit stupid at the moment, so hopefully we'll get it tied up before it goes all together. So, right, first question is from, is that Pure Reality? It's how do we measure the speed of light?
What experiment you do, in other words?
Say 3 o'clock.
Yeah. Bob, you trying to answer?
Well, guys, there's a couple ways that you can measure the speed of light, and that's how it was determined. The first one was observing the orbit of Io around Jupiter and comparing it to the position in the orbit of the Earth. And they found that it took a certain amount of time. Light took a little bit longer when we were further away from Jupiter than it did when we were closer. We knew the distance that we were further away and came out to like 22 minutes or something or other like that. And from that, they calculated the speed of light. The other way that they do it is with rotating gears and rotating mirrors to try and do an interference pattern. I actually may do a video on this. I think it's kind of an interesting subject.
All right. Hopefully that's good enough for who asked. Let me see. Next question is, I think, from Gently's channel. No, wait a minute. It's a bit mixed. Yeah, Gently's channel. Are galaxies moving, or is the space between them expanding?
Both.
Jump. Like there's you can do in a microwave to measure the speed of light yourself.
Right, if you know the frequency, I think they tell you the frequency on your microwave, don't they? And then you put something in there. Don't put it on the rotating thing. Then you put something that's very sensitive to temperature and put it there for a few minutes. And you can see the wavelength, and you can see, if you know the frequency, you've got the wavelength, and you can just multiply those two together to get the velocity. But obviously, the experiment, the thing that Bob was talking about, the motion of Io, or I can't remember if that's that or one of Jupiter's moons, that was done, I think, in about 1700 or something like that, where they came up with I think it got within about 10% of the speed of light with that, which is not too bad, and then gradually got better and better.
I quite like that. There's a homebrew way of doing that. That's quite cool. Okay, let's see. We've got a question from Channel Q. Ask the Rumpus to explain to me how it is I would age slower in a black hole. I don't believe time works that way.
Wait, I just have to point out we skipped a question.
What was that?
You asked the question, and then something about galaxies spreading.
Oh,
yeah,
right. So I asked that, and then you went back to the speed of light. Are you experiencing some time dilation, sadly?
Was that it is the case that galaxies are both moving through space and that the space between them is expanding. They're both true and not really related.
and I've now forgotten why we know that space is expanding. I've forgotten what experimental evidence we've got for that. Because obviously we know that things, for instance, very peculiarly, we know that things can move faster than the speed of light because space can expand faster than speed. So in fact, the things that we're looking at the moment at the very limits of the observable universe are now moving further away from us than the speed of light, and we'll never see them again. It's really weird. And as time goes on, eventually the only stars we'll see surrounding us will be our local galaxy. The rest of them will be moving faster between us and the speed of light. And that's due to the expansion of the universe, not speed of light. So, but obviously galaxies themselves are also moving in strange ways. I mean, for instance, we're moving towards Andromeda at quite a fast speed. So that there are local, and obviously the redshift obviously tells you that the relative movement, just using the Doppler effect, with redshift we can tell that things are moving away from us. That's the expanding of the universe, I suppose. Yeah. So, but also you can tell locally. You can do other things to say that obviously galaxies are moving, and we can see them moving together. We can see two galaxies actually hitting one another, like either the shotgun or the bullet galaxy, whatever it was, of two colliding galaxies, which I was talking about with the dark matter thing. We can see that obviously galaxies are moving relative to one another. We can see them colliding, so we can clearly see them moving around. And the redshift tells us about the expansion of the universe and the expansion of space-time. And as I say, that's faster for the things we can see in the far distance than the speed of light, which is all a bit weird, but we'll go into that.
Yeah, the galactic recession velocity as a function of its distance from us. That's how
Hubble's
we know.
law. Yeah, Hubble's law.
Yeah.
Excellent. Okay, I think there was a follow-up question which has been retracted now. Let's see. So yeah, so the next one.
Channel Q's question about
was Channel Q.
We're missing.
Sorry, I went past it there. Yep. Ask Rumpus to explain to me how it is I would age slower in a black hole. I don't.
Well, you age more slowly at the bottom of the Eiffel Tower than you do at the top. So don't go charging up the Eiffel Tower for a romantic encounter. Stick them at the bottom, and then you'll be that little bit younger. And similarly, if you but then the surface of the Earth is actually the place around here, and with the maximum gravity, if you go further in the hole, it actually gets less. So you're well placed at the surface level to minimise the passage of time, unless we can find a new local planet that's slightly denser, slightly higher gravity.
Okay, we've got a question from Maxwell Smart, which is, how do you calculate the mass of a black hole?
Ooh, I can do the flat Earth version. So first you go there, and then you scoop out like a cup of black hole, and then you need to measure the width of the black hole, which you have to use a ruler. Then unfortunately you have to use the Freemason Jesuit math to calculate the volume. I don't know. It confuses them. So that's it.
That is a brilliant answer, MC2. That is a fantastic answer. That highlights the logic of it. Yeah, that's really excellent, actually. That's the best answer so far, in fact. Oh, that was really good.
Well, the answer, of course, is that we measured the behavior of the material near the black hole. Right?
Here's a question for people. If the sun was turned into a black hole, what effect would it have on our orbit? Anybody, any ideas besides Professor Dave, who clearly knows?
Wump.
No. Sorry? If you turn the sun into a black hole with the same mass...
Wump.
Sorry, Bob, we can't hear you. Bob, we didn't hear your answer.
It won't have an effect, that's what you're saying, I think.
Okay, and that's correct, yes.
Yeah.
So the fact that you'd measure the black hole exactly the same way as you'd measure the mass of a star by...
But the Earth would keep orbiting as it orbits.
There was Khalid in chat was wanting to get me to mention something. He was saying, can you talk about how muon decay proves time dilation?
We hit that one, didn't we?
Perhaps he wants it again?
Maybe, but just if you can, he maybe wasn't here, so if he's still here, it may be good just to quickly mention that.
If a particle decays in a certain span of time, then you should be able to calculate how far it could travel laterally before decaying. And muons that are formed in the upper atmosphere because cosmic rays strike a particle and a muon forms. If it can make it to the Earth such that they're detected by instrumentation down here, and that distance is dramatically longer than how far they should be able to travel, then they are able to traverse that distance because they're experiencing time dilation. Time is moving more slowly
measure
for
how
the
velocity, how we can measure the speed, so we can measure the speed of this particle, so therefore we know what distance it's travelled. And then we think, hold on, that's taken them this amount of time, and that's not right because we know this particle only exists for this long.
Mm-hmm.
I think that's it. Just double check. Is that everything, Tommy? Just while I wait on Tommy getting back to me as well, we've obviously got a good panel, I guess, and again I want to thank everybody for coming, but obviously all your channels are being shilled in the description, but there is a channel that I would like to mention. He was in here earlier, I don't know if he's still here. It's I Can Science That. He doesn't do videos very often, but he knows his stuff. He does great videos. So anybody watching, anybody the panel interested, go and check him out. He does some interesting, explanatory sort of science education stuff.
And our missing panel member, you want to mention him too?
In a sense, there's two. As I say, SciManDan was meant to be here tonight, but he had a family issue, so he's not here. But again, he's well known, and he's mentioned in the description. Also, Conspiracy Cats was invited, but was unable to make it because his commitment at work. And in case anybody doesn't understand why, you guys all share something in common. You're either science educators or you're people who believe in promoting science in some way, shape, or form. So I thought it would be good to get you all together in one place and talk about this topic, because it is obviously a common topic that keeps coming up. And I think we've shown in the discussion that there isn't really a definitive yes or no answer to these kinds of questions. And it's not a contradiction in what we're saying. I think that's the way it needs to be from the flat earth point of view. It's either you either know something or you don't. You've either got a yes or a no. It's black or white. There's no grey areas. Whereas, as we've already said, it just doesn't really work like that in general with science. You get the best possible answer you can have, and you have predictive models and so on. And until something comes along to shift that, then that's the way it goes. I think Tommy's saying to me we've got something else. Give me a second.
Let me comment on that.
First showed up with a silly question.
Sorry, I'm sure you can imagine that it's not going to be the greatest of questions from Earth is seriously flat.
Oh, God. No. Whatever is it, stupid.
What scientific experiment can I perform to demonstrate that the Big Bang Theory is real?
Go study astrophysics, and you'll do them. You can't do it at home.
Go there.
Yeah, a tutorial devoted specifically to the empirical evidence for the Big Bang cosmological model. I would direct anyone to that one. It cites the various different and agreeing data that corroborate the age of the universe and the Big Bang itself.
And even more so, you can actually confirm as best as you can, almost to a reasonable degree of certainty, the inflation part of the theory, because the shape of the cosmic microwave background radiation temperature variations. There were many theories that predicting what the pattern should be, and inflation theory gives us the pattern we actually see. So we've actually very confident we even know some of the early processes as well.
The isotropy, yeah.
And just the shape, the little sizes of the little of the variations. There are certain angles in there that are predicted by the inflationary theory. And I see that Ranty Flat Earth is asking about how we can have vacuum next to. There we go. Yeah,
I was waiting for the opportunity to mention it. I mean, they just parrot each other, and it's been said so many times. It's the entire topic of this discussion. Gravity.
Well, some of these questions are so absurd. You have to wonder if they're serious with them.
Hey guys.
Oh, yep.
Hey guys. I'm thinking about this question from the Earth is seriously flat about the empiric evidence. for the Big Bang. And I have a question for him. Specifically, what evidence would you look for that would say yes or no? So why don't you explain the Big Bang Theory and what would prove or disprove it?
Well,
they're going to sit down and ask all these questions that they don't understand in the first place.
Well,
so
we know this stems from the whole scientific method
it,
nonsense.
Yeah, I like to put it right back to them and say, okay, well, great, explain it to me in your own words, and then you tell me an experiment that would say yes or no on it. And then we'll sit down and see if they've done one like that.
Well,
sorry. The problem, though, is that like a layperson won't be able to come up with the idea of the CMBR, right? We particle physicists, theoretical physicists understand what happened in those first few moments of the universe, and that the recombination era, right? The recombination era would leave a remnant of electromagnetic radiation, but that's very
kind of the point that I'm making. He doesn't even understand the question.
Well,
right.
I think that's a bit unfair. I think he can say what evidence. A question is reasonably clear. What proof do we have?
Well, Rumpus, I'm going to step in and say, as I was saying, it's not really the case, because what he's actually doing is just parroting this scientific method stupidity that was started by QE and Sleeping Warrior and whatever.
Well, it doesn't matter where the question came from. It's still a valid question.
No, but that's why it's worded that way. That's what he's meaning by that question is, what does he have to wiggle? What's your independent variable and all that nonsense?
It doesn't matter where the questions come from. It's a valid question. What is the evidence we have for the Big Bang? And obviously the big one is the expanding universe. And if you reverse that with the redshift, you end up with all the theories then say, well, actually, it came from a very small point. And then we can have all these other sort of theories about the recombination and things about being able to see the cosmic microwave background radiation and all that. But if you bring those together, the question itself is a perfectly...
Hey, Rumpus, do you think he even remotely understands any of that?
No, he doesn't. No.
That would be a question.
But the question is valid. But the question is valid.
Anybody can understand it. So it all came from a spot, right? I feel like that's fairly intuitive. That may be the only aspect of the model that is explainable to a layperson, but it is very easily explainable.
Yeah.
Right?
Yeah, it's pretty obvious bit of deduction to say if something's expanding.
Now you have to then make it very clear that that's not all we have, right? It's not just, that's not it. It's just that's the only part that we can explain to you that will make any sense, right?
Can I comment on that?
Do we want to deal with Ranty's question about pressure and vacuum and things?
But let's Emily say what he's got to say, and then we'll get to that. Okay.
Yeah, this goes all the way back to what the scientific theory is. We take a bunch of observations and we induce an idea like about why these observations exist. But then at some point you come around to developing a model, and then the deductive part of science is when you start testing that model, testing them, and that's where deduction is. But science is in its nature inductive in the pursuit of the theory itself that's going to explain this thing. It's not mathematics, and that's how flat earthers approach it. Flat earthers approach it as science should give us a deductive proof of reality, and that's just not that's not the domain of science. The domain of deductive proofs is mathematics. That's where it is. That's why we have mathematical models, though. I mean, it kind of keeps us sound.
You make falsifiable predictions and then try to falsify them.
Yeah, not prove, which is one of the big mistakes that keep getting made.
Proof is for mathematics and logic.
Yeah,
that's it.
Absolutely right. We don't know. We're not being surrounded by invisible green pixies or in the Matrix, and therefore we can't rely on anything. But maths is something we can say, right, 1 + 1. We can define maths, and that's why you can deduce it and prove it. Whereas with science, it's all about our perceptions of the world, and we could all be being tricked, as far as we know, by invisible green pixies or God knows what.
Right, so I hate to do this, but Dave, we've had the classic question posed to us by Ranty Flat Earth in the chat, which is, how can you have a gas pressure next to a vacuum? And he would specifically like yourself to deal with that question.
Sure. Because gravity exists, right? So my favorite is they will cite the second law of thermodynamics without knowing what the second law of thermodynamics is. Second law of thermodynamics has to do with entropy. It is about the dispersion of matter and energy. So a gas will tend to disperse unless it is under the influence of a force. And so I covered this in my last video. The confusion stems from the fact that flat earthers think that vacuums are synonymous with vacuum cleaners. That's basically the crux of the problem here. When in fact vacuums don't suck. So the vacuum of space is not sucking anything into space. If you were to turn gravity off like a light switch, then the atmosphere, the molecules in the atmosphere would drift off into space. But there is a downward force holding them here, holding them on the Earth, and that is why we see a pressure gradient, right? So I really they cite the second law of thermodynamics to pretend as though they have a basis in science to ask that question, when it's really just a misunderstanding of thermodynamics. And the answer is one word. The answer to the question is gravity. That's it. That's the end of the story, you know. So.
And of course,
the question that I have for Ranty: if you believe the second law of thermodynamics is correct, why, for some reason, is the law of gravity different?
Yeah, Newton's law of universal gravitation. I mean, yeah, it's.
If you accept one, why can't you accept the other?
and let's not forget, at the upper reaches of the atmosphere, there is no high pressure, low pressure, very, very low pressure, next to an even lower pressure. And of course, space itself, even deep space, has something like, I think, 100 atom per cubic meter. And so there's never any perfect vacuum anywhere. But actually that is actually a better vacuum than we can create in a lab. But I mean, there's never a case of having a high pressure thing next to a very low pressure thing. The difference is always very, very tiny. There's just a density of pressure something, and there's something very, 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 very close to it next to it.
Honestly, I'd like to take this a little bit further, because it's not just flat earthers who cite the second law of thermodynamics. It's also creationists and things like that. And they try to use it to imply that order cannot be spontaneously created. But this is absurd. Just put water in an ice tray and put it in the freezer. You get an ice cube, right? An ice cube is ordered, right? Why? What is happening? Because spontaneity is not just entropy; it's also enthalpy, right? The electromagnetic force, the attraction between these molecules, is creating the ordered structure spontaneously. Order can arise spontaneously. So this second law of thermo, as just sort of a catch-all, what you're saying can't happen, really just stems from a misunderstanding of that law, plain and simple.
And gravity is a fantastic ordering process, isn't it? It's the cause of stars, planets, galaxies. It's an amazing ordering force. And basically, they need to get to grips with the idea that forces can overcome entropy. It's very simple. And that's what's holding these molecules under atmosphere. It's what keeping a brick together, and that's not pooling into some mess on the floor. It's what keeps not everywhere, and covering the whole of the surface of the planet in a uniform way. Forces are doing opposing entropy. Entropy can't invalidate forces.
Just to tag on, because I've been asked to mention this, Crow XE made a simple sort of logical statement, which is that pressure keeps dropping with altitude, which is a fact, and we need a proof that this stops happening at a certain height, or else it will end up as a vacuum. Which obviously makes logical sense.
Yeah, it can't just stop. It's going to carry on getting less and less and less.
Yeah.
It's experimentally proved. That's what happens. We send up balloons and we find out that that's what happens up there. We don't need to even theorize about it.
His conclusion is a little bit different. He's saying eventually it gets to a vacuum, like a pure vacuum. And maybe, I don't know, maybe I'm interpreting it wrong, but I was thinking that he's doing subtraction instead of division in figuring out what the pressure is going to be as you go farther.
Yeah, Cullen's reasonably clever. I think he's not suggesting it goes down to zero, but yeah, obviously it's a fraction. It doesn't follow a minus. It just becomes percentagely less as you go up. Yeah.
I mean, the thing is, there's no way the people that are quoting the second law of thermodynamics have the first clue what they're really saying when they say that. But the reason why they also think that it works stems from that root misconception that comes from flat Earth, that the atmosphere or gases are somehow magical and they just float away and they aren't affected by gravity. So that everything with maths is going to be affected, but they seem to, they see these small scale demonstrations of a gas being released into a very sort of small volume area, and they can't seem to take that up to the level of the actual atmosphere of the Earth, where gases dissipate, thin out, the gradient, etc. This is as if they're just going to expand and expand forever because they go up above their heads.
Why do gaseous particles float? Why do oxygen molecules and nitrogen molecules in the atmosphere float? Because they're super tiny molecules, and just the ambient heat energy of the atmosphere is enough to impart upon them enough kinetic energy to float around. And the distribution, right? The distribution of kinetic energies of the molecules in a gas, fewer and fewer of them are going to have enough kinetic energy to go higher and higher and higher, right? That's partially what explains that gradient. But yeah, molecules are so tiny that given them a little bit of energy, a little bit of kinetic energy, and they can float. Right. That's why gases float.
You're making exactly the point I was going to make as well, Professor Dave. If you imagine that a typical oxygen molecule, I think, is moving at about 3,000-4,000 miles an hour. So, and remember, the gravity effect, it doesn't matter how big or small you are, gravity affects you effectively in terms of the acceleration upon its same. So if you start off thinking of a little molecule sitting on the surface of the Earth doing 5,000 miles, or a car that was moving 5,000 miles an hour, it's pointing vertically upwards, how far would it get? Remember, it has a spring on it. All these molecules that are above, they've got little springs of gravity pulling on them. So imagine you launched up your car at 5,000 miles an hour, and imagine there was a vacuum there, and it's going up. How high would it get? And it would get to about where the atmosphere stops.
Yeah.
Because they've got 5,000 miles an hour kinetic energy.
Hydrogen or helium, it's not stopping there. It's going to keep going.
Exactly. That's even faster. So helium is moving, hydrogen is moving, I think, about 25,000 miles an hour. Right. And that's moving so quickly that it can actually escape. It doesn't matter. There's little springs that the gravity is pulling on it are so only strong enough. It would have to get to the other side of the solar system before the spring would actually cause it to work, because it's not quite linear, of course. It's not quite a spring, it's not linear, it's inverse square law. But it's effectively the same thing. It's like climbing up a hill. Basically, the atoms are sort of climbing up this hill, and they get tired up, and they turned all their kinetic energy to potential energy, and to do that for something that's doing 25,000 miles an hour, it can actually get up to the other side of the solar system.
It is not a coincidence that the root mean square velocity of a molecule is inversely proportional to its mass. The lighter it is, the faster it goes. Yeah. Right. And that's with F equals ma as well. If you have a force, if you have an equivalent force, the smaller the mass, the more that will be accelerated. Right. Smaller masses are accelerated to a greater extent.
Yeah. So the hydrogen molecules are moving about 25,000 miles an hour. We've got in our air, oxygen molecules moving about 3,000 or 4,000 miles an hour. So that's why the hydrogen molecules, if you, shoot them up, imagine 25,000 miles an hour aeroplane pointed upwards, it's going to escape the Earth, whereas the 5,000 mile
travel velocity that exceeds the escape velocity of the Earth. So the Earth can't hold them. That's that whole the moon is in our atmosphere bullshit too. Oh my God. So hydrogen leaves the Earth. So there's a tiny bit of hydrogen.
There is another confusing issue, of course. There's the ionosphere, because when they do actually get molecules do actually happen to get up very high, they're hit by the solar wind and ultra powerful UV light, which actually splits them apart. It actually ionizes. It causes oxygen molecules to break apart. And that means they're actually getting another boost of energy, which means that they can start shooting off and perhaps make their way off to the moon or something. So they get an extra, like a sort of turbocharge when they get up very, very high. But once you get below the ionizing layer, then the sunlight, because most of the sunlight, of course, just doesn't actually interact with the gas molecules, which they all interact with the Earth, because that's the reason why you can see through the atmosphere, because light is not interacting with it. It's interacting with the ground. So the heat energy is effectively down here, and the molecules are effectively not being energized by the light. But there is a couple of bits where these the ultra high frequency UV light at the top does actually interact with the molecules and does ionize them, so they get an extra boost.
When I first heard about the moon is in our atmosphere, I said, now there is a scientist that is trolling flat earthers. It's gotta be.
It's the media. It's the clickbait era. This is what I was getting at earlier. I really want to try to influence media outlets as much as possible because they're saying that so people will click on it.
Yep.
Then if you read the thing, and it says, "Oh, okay, but others aren't going to read that. They're going to look at the title and they're going, "Oh, the moon is now in the sky. Scientists said it." So
you're fighting the internet.
I know, but it's just if I could exert some small influence on the way people are reporting science, that's what I would say is just you're doing damage to the public by misconstruing something so to increase your click-throughs, and you can't blame them because it's just that's the era we're in. But somebody has to make a concerted effort against this, or it's going to get worse.
There's some PR guy behind the scenes that's going, yeah, that's exactly what we're doing. Of course.
Oh, of course he knows. Yeah, they know. They're not dumb. They know what they're doing. They know.
The way you combat that is by educating the audiences to understand what it is, what they're saying.
Yeah. The other side of it is just educate the public as well. But both of these things are hard, right? To drive against a profit margin and to forcibly educate people, these are both very uphill battles.
Yeah.
Right.
I hate to do this, but I need to jump in with another one. It's a Hoaxley troll. Sorry, Dave, you probably don't know what that means, but everybody else will. Professor Dave, what observational evidence is there that the Earth is orbiting the Sun without using and affirming the consequent fallacy?
The consequent fallacy. Why am I being singled out, by the way?
Why? Come on. Why do you think?
Well, I mean, the title of these is the night sky. That would be the answer. I mean, stellar parallax. Everything we see about the sky, the apparent positions of everything in the sky. I mean, the validity of a model. If you want to look at the round Earth model and the power that it has, and well, specifically the heliocentric model of unifying all observations, right? If we want to explain what night and day are, if we want to explain what seasons are, if we want to explain anything about what stars we see, when we see them, how we see them, all of those things make sense in the context of one thing. The Earth is rotating on its axis, tilted from the orbital plane and going around the sun. That's it. And if you do that, all of the things we see make sense. And that really is the simplest answer. You can get more technical by talking about stellar parallax. But they don't like that, right? They'll just say, well, I didn't go look through that telescope, so I don't know that that's true.
Can I add?
My answer is, what months can you see Orion in the night sky?
Mm-hmm.
There's two things we know. We know the relative movements between the different bodies, especially the major bodies, the planets. And we know that there's a speed limit called the speed of light. So the universe can't be rotating around. It's because before you get out to Neptune, things are already moving faster than the speed of light.
Yeah, absolutely right.
Well, they would argue that those things just aren't that far. Right. It's all up.
Oh, yeah.
But look, I mean, if you want to put it in a historical context, because this is how science went, right? You had Ptolemy and the geocentric model. I mean, let's just, for the sake of argument, let's assume a round Earth. Let's assume a round geocentric model, right? You had Ptolemy, and Ptolemy did fine, but he couldn't explain things like retrograde motion. Why? If everything's going around, why does the planet go like this? Oops, and then it goes back, and then it does this. And so he came up with these epicycles, right? And so now things are rotating on circles on the circular orbit, and it just got more and more and more and more complicated. And then all it took was the Copernican revolution to say, you know what, everything's going around the sun. And then, whoops, wow, that works way better. It's way simpler. The positions of everything in the sky matches predictions immaculately, except for Mercury, which was explained later with Einstein. So it's just about how do we explain what we see. The thing that does it the simplest and the most thoroughly and the most accurately and precise, or the most precisely, I should say, is probably right, and that's heliocentrism. There's no arguing that,
Occam's razor.
Yeah.
Right. As you know, MC Toon's kind of his timing's pretty good. I think we'll probably start wrapping things up, but I was trying to keep all the questions on topic tonight. There was one question that was off topic. I don't have it in front of me, but I think I remember the gist of it, so if I can be corrected anyway. Which is, why does nobody talk about abiogenesis and in flat Earth essentially? Let me see. I'll see if I can find it. Sorry, it's not. I thought I had it there, but
this is because flatties, about a third or something of the flatties are religiously based, and therefore they start bringing all these other issues, religious issues, into the subject matter of talk, which of course are irrelevant to the job. It's a geometrical question, therefore it needs geometrical analysis, not religious analysis.
Yeah, so that was it. It was given flat Earth is bound up in creationism. Why is there so little discussion of abiogenesis by Globers? But I think that
this is a geometrical problem.
It is a geometry thing. It's not really about their, fundy.
Well, chemist, I love talking about abiogenesis, but it has nothing to do with this at all. I mean, I'll happily talk about it, but what does it have to do with this?
Yeah, I think. I mean, obviously, if it crops up, if you're in an individual panel with certain people and they're going to go that route, then I suppose you can bring it up, but. Mm-hmm. As a rule, the idea would be to steer away from that kind of stuff because it just isn't relevant. I know, and I'm sure MC Toon and Soundly can chime in on that from the Christian perspective.
I'm trying to remember Christian's perspective. It's not nearest. No point globe or discussion flat Earth versus. But obviously, I think God created life. But is it likely that He created it through the mechanisms of nature? I think He did. So there's going to be young Earth creationists that say no, He created it 6,000 years ago, and boom, poof, Adam and Eve came into existence. I just don't agree. But who can actually know? Nobody was there. I mean, an all-powerful God could instantaneously create everything, making it look old 6,000 years ago, I guess. But I don't think He would have, based on the biblical God. He's not a deceptive entity. So why would He make everything look old unless it actually was old? I think God created it 4.5 billion years, or what's the age now? It's way old.
Of the Earth? Yeah, 4.6.
Yeah. So. Well, he created the Big Bang,
13.8
billion years.
0.7.
Okay. So,
or 0.8.
Back to the Big Bang.
We don't know we don't know exactly when. I don't
understand why people limit God. To be honest, so, I mean, why couldn't God just say, "Okay, I'm going to create a Big Bang, and this is how everything's going to lay out." Boom, and it works.
Yeah, and that's precisely the kind of God that no one can argue with.
Minecraft programmers figured out how to do it, and why can't God? And that's what I'm saying.
Yeah, I've never understood that mentality of being resistant to things being possible under God. That just because you're saying that He's basically capable of everything, but then there's certain aspects you go, well, that doesn't fit with my beliefs, so I'm going to say that it doesn't work. But surely the answer to everything is, well, God can make anything possible, so how can you argue against it? Evolution being the prime example.
Yeah, the problem with those debates is there's no answer. There's no conclusion. One person thinks God did it. The other person thinks nature did it without God. Okay. I mean, where do you go from there? There's nowhere else to go. So, those.
I think I accidentally cut Dave off a bit there. Sorry, Dave, were you going to say something?
No. I just, my only contribution is wherever possible, I like to try my best to explain to lay people the mechanisms by which abiogenesis absolutely could have happened. We don't know what happened, but a lot of people try to present the idea that it is impossible. It's definitely not impossible. It just to understand how it could have happened requires reasonable amount of knowledge in organic chemistry and biochemistry and biology. So I try to teach that whenever possible. But certainly we don't know precisely what happened, of course. But I just like to show here are some things that may have happened, and it's not as outlandish as people suggest, right?
What was the name of that experiment that was done?
And the
You're
fission is generating amino acids in the test tube.
Yeah,
Or
yeah.
And the
Yeah.
fission is,
I mean, that to me is enough. You know, it's enough of an indication that these kind of things are possible.
quite a bit more than that, actually. It's only generated a few of the amino acids, and it's quite a lot more to generating a cell, for instance, is a very, very, very tricky thing. But then again, if you've got 3.5, or you've got a couple of billion years to play with to do it, you know, and there's a lot of energy in the system. You know, we know that, and as opposed to secular thermodynamics, if you've got lots of energy coming to the system, your entropy decreases and you create order. And part of this creation of order is life.
Mm-hmm. Yeah, you have to explain how biomolecules polymerize. But I think that if my favorite hypothesis is that mineral tide pools. You've got some heterogeneous mineral surface that can certainly catalyze the polymerization of biomolecules. If you study just the tiniest bit of organometallic catalysis, it's extremely clear how that could have happened, not only spontaneously, but also in a stereospecific manner, right? We only have L amino acids, or we only have, this certain handedness to nature. It explains it perfectly. Do we know that's what happened? No, but it totally could. It makes perfect sense to me that could happen that way.
I think a lot of people put too much importance as well on the idea that we need to understand how something did happen in order for it to have happened. I've never understood that mentality either. It's as if if we can't figure it out through science, whatever, then it's not possible, which is just a ridiculous way to look at the universe.
Mm-hmm. Yeah.
I think we should maybe consider wrapping up, and I know
wants
to get away. Sorry, you roboted a bit there, Dave. What was that? Sorry.
Oh no, never mind. It's not even worth repeating. Go ahead.
All right, cool. So yeah, as I said, maybe just wrap things up. MC Toon does want to get away, but MC Toon, did you want to chip in on the Christian perspective?
Sure. When you look at the creation story in the Bible, Genesis, it's good to look at the intended audience, and these were people that were slaves for generations. They weren't very well educated, most likely, and so laying out some quantum physics description of what happened isn't something that you can do to them, and doesn't really matter all that much. It doesn't claim to be a science book, and if you treat the Bible as a science book, you get weird things like pi equals 3. So to take it as more of an allegory, I think is a pretty fair way to look at things. At least it works for me, and it works for an awful lot of people. So I'm happy with that. And then to look to science to say what really happened.
Right, so before we finish up properly, I guess getting back on topic for one last time, would you like to summarize again your thoughts on gravity, just to round off? Sorry, maybe I should pick someone to go first. Professor Dave, would you like to go?
The active force between all matter that is either a fundamental force or an apparent force due to the curvature of space-time, which will potentially be further refined given the work of frontier theoretical physics.
Okay, MC Toon?
Gravity pulls things together. Mass attracts mass. And I really like the fourth dimension being time, and we're traveling through it, and there's topology as a kind of a simplified way to explain the why behind gravity.
Cheers, Soundly.
I mean, it's basically what I've already said. There's a group of observations we see happening in reality. We know they're real because we first observed them in reality. Then we give them a name. We call them gravity. So it's really that simple. I think the question that they're asking is intentionally from the reverse direction to make us question the word or the name that we've given in a phenomena, and then somehow to discredit the phenomena itself. But the phenomena itself is easily observable in reality. I mean, point your telescope at Jupiter, watch the moons go around. There you go.
Okay, Bob, if you're still here, you want to go ahead?
Gravity is an observable attraction between masses. Newton described what it does. Einstein described it.
I don't know. Did that cut out for anybody else there?
No, yeah, I think you got the problem there.
Yeah, I think I got the problem at my end. I think my laptop's a bit flaky or something. Okay, so that leaves yourself, Rumpus, if you want to go ahead.
Yes, people who dispute the existence of the force of gravity just need to go and get on some scales. That thing, that the little, remember, scales are force meters, and the force that they're showing you is the force of gravity in our world. The fact that we've got some rather complicated explanations of how that comes about is really irrelevant to the fact that it is in our world present, and will do you a lot of damage if you allow the Earth to be attracting you without an obstruction in the way from a great height.
Right. Okay, so we've had plenty of feedback from the chat saying that it's been an awesome panel, and to thank you, all very much for doing this. And I echo that. I really appreciate you guys coming in to talk to me, especially because there was just no warning. And I know some of you are pretty busy with your channels or busy with your vacations and so on. So that's been really good of you to actually agree just to be here. It's been interesting as well just to see where everybody stands, and it's kind of, I think overall everybody agrees with each other. Although there's some questions around gravity, the general consensus is there. It was not a bad thing. Before I actually end the stream, this was really just a one-off thing. I just chanced my arm and asked everybody, but I guess I should ask if you guys would be up for doing it again sometime, not necessarily an attempt to make it regular, but just randomly every now and again, maybe getting together and doing something similar.
Sure.
I'm game.
I'll do it.
Excellent. And hopefully maybe get Dan and Katz on at some point. Right, I'm going to end the stream if you guys want to hang about for a second. And again, thanks to everybody for showing up to listen in. And hopefully it's been interesting and informative. Cheers, everybody.
Thanks. See ya.